Hello everyone, this is Umang here, and with me here is Arbaz again. I hope you all had a very good session yesterday on the Formula Car steering design. If it was good, today is going to be great. Okay, because today is where the all of the key content is going to be. Okay. So without further ado, I will move it to Arbaz sir. We will have a quick review, we'll take a few doubts, and then we will jump on the new content. So over to you, Arbaz sir.
Yes, thank you, Umang sir. And hello, everybody, once again. It's good connecting once again. And I hope yesterday's session was pretty clear. Still, I will do one thing. What we studied in yesterday's session, I'll give a quick overview about all of that. And then we'll take a short doubt session where I'll try to answer like at least 5 to 7 doubts regarding yesterday's session. And then we can start on today's session. And the structure for today is going to be we'll start with today's session. There'll be a first part of the session where I'll be talking about the generalized Ackerman steering geometry calculation, like I told you yesterday, because you need to have a basic understanding of Ackerman steering geometry before learning the anti-Ackerman steering geometry. So we'll get that out of the way first in like first half of the session, and then I'll take a short doubt session again based on that first half, because I want you all to be clear on the first half, then only we can move on to the second half. And in second half, there will be studying the anti-Ackerman geometry, which is actually used in Formula One races. So yeah, that's going to be the overall structure from my side. After the session, again, there'll be one doubt session, and then you'll get the scholarship forms. So make sure you stick around for all of that. And let me just go through. So I'll just start sharing my screen, and I'll just go through yesterday's session. Okay, so yesterday these were some of the things that we studied. We first looked at the function of steering system, the types of steering mechanism, then the detailed explanation of these mechanisms. Then we went to types of steering geometry, properties of Ackerman and anti-Ackerman geometry, and then we lastly saw the table in which we saw how to select a particular type of steering geometry and mechanism for your particular type of vehicle. Now, what is the steering geometry? So here we learned the function. First function was to convert the rotational motion of your steering wheel to the turning motion of your road wheel, and second function was to reduce the human effort. And these were the two main functions. And then we moved on to seeing the types of mechanism, which were divided up into primary and secondary. And primary ones were mechanical, which help satisfy the first function, which was turning the rotary motion of your steering wheel into a turning motion of your road wheels, right? And then we had the auxiliary steering system, in which we saw electric and hydraulic steering system, which were basically adding power to your steering system and reducing the human effort, thereby satisfying the second function. Then we saw what was the rack and pinion mechanism. This is something we'll be going through once again today, because we'll be doing calculation for rack and pinion mechanism. In a sense, we had 5 parts. So number one being the steering wheel, number two steering column. Then there was the pinion, which was meshed with the rack. The rack was connected to the tie rod, which was the pink lines you see. And then the golden part was the steering knuckle. And this is how the working was, a short animation. Then we saw the functions, the features. It was simple in construction. It's economical, uncomplicated. It gives higher mechanical advantage to the driver, and it is compact, hence used in almost all of the commercial cars. Then we saw recirculating ball mechanism, where we saw that its working was similar to the worm and worm gear, and it uses ball to maintain the contact between gears, thereby reducing the backlash and also reducing the effort required to move. So that was the two main functions of these balls. Then we went to bell crank mechanism, which was the simplest form of steering mechanism, where you have a steering column connected to which is the bell crank. If you follow my cursor, this is the steering column, the bell crank, and to the bell crank directly we have the tie rods, which are directly connected to your Ackerman arm or your steering knuckle. So what will happen when you turn the steering column, the Ackerman arm, the drop link will rotate about the center point of your steering column, and it will push the tie rod left to right, and the tie rod will in turn push or turn the wheel in this way. So this was the working of bell crank mechanism. And then we studied these auxiliary types of steering mechanism. First was hydraulic system, electric powered hydraulic steering system, in which we saw that the rack was attached with a double acting piston cylinder arrangement, and to that piston cylinder arrangement there was some hydraulic fluid supply, and the supply was taken care by the rotary valves and the pressure pump. When you rotate the steering wheel, rotary valve open in such a way that the flow would happen in the desired direction, and it will push the tie rod in the desired direction. And this was about the electric power steering, and this is how it was kind of working. Next thing we saw was the fully electric steering system, in which we saw whenever you turn your steering wheel, there are two ways to reduce human effort. First was to move the rack itself, and second was to rotate the steering column. So in this method, we try to rotate the steering column by applying a motor with a reduction gear to it, right? And ECU was introduced over here. ECU takes sensors from it. ECU takes inputs from all the sensors such as vehicle speed, steering angle, and torque sensor, and depending upon that, it gives output to the motor as to how much speed, with how much speed it should rotate, and at how much degree or how much angle it should rotate. And that motion was given to a set of reduction gear, which was then connected to the steering column. So that was how the working of fully electric steering system happened. And you can see over here, this was the motor, and then this was the set of reduction gears which would work. And that was for the steering mechanisms. Then we went to types of steering geometry. Mainly, we talked about Ackerman and anti-Ackerman geometry. And in Ackerman geometry, we studied that the internal or the inner wheel turning angle is higher than the outer wheel turning angle, and it causes an instantaneous center, which is this point over here, which will lie on the rear axle. Right, and we also saw that the Ackerman arm or the steering knuckle should be pointed in such a way that the intersection of these 2 points should be on the rear axle at the center point between the two wheels. So that was about the Ackerman geometry. And exactly opposite to this, we saw anti-Ackerman geometry. But before going to that, there was a small animation that I had showed, that inner angle will always be higher in Ackerman geometry, right? So you can see over here, when it turns on the right side, this becomes the inner wheel, and you have the higher turning angle at this point compared to this one. But when we go on the other side, this angle becomes higher than this angle. So that was what we saw in the Ackerman steering geometry. Then we moved on to anti-Ackerman geometry. It is completely opposite to your Ackerman geometry. In this type of geometry, the outer wheel will be having the higher angle. You can think of it as a mirror image when you keep a mirror in front of your vehicle. Okay, so that's the mirror image kind of geometry that happens in anti-Ackerman geometry, and it is used in Formula One races. It needs high precision to design, and you need to know a lot of data. And also, we had this video in anti-Ackerman geometry also, where if you turn a wheel on one side, whichever is the outer wheel for that turn will have higher degree of turning or higher angle of turn. Same thing happens on the other side. This one becomes the outer wheel, and here you can see the higher angle. And that was about the anti-Ackerman geometry. Then we went through the applications of various mechanisms. We had commercial vehicles, small trucks. They both had the same kind of mechanism and same kind of geometry for same reasons, because you need to have durability and reliability. Heavy vehicles, we wanted to reduce the steering effort as much as possible. That's why we started using a recirculating ball mechanism with Ackerman geometry. And we used Ackerman geometry to reduce the wear in the tire. When it comes to a race car, we use rack and pinion because it's sturdy and it is reliable, and you can attach power steering on rack and pinion easily. And we go with anti-Ackerman geometry to achieve higher speed, because you can take advantage of the slip angle. Now, when you come to luxury car, we saw that we use recirculating ball type mainly because we want a smooth operation. And again, luxury cars are not going to go at high speeds. That's why we use the Ackerman geometry. Coming to the all-terrain vehicle, we use rack and pinion because it should be able to sustain high shocks, heavy shocks. And that's why we used a sturdy rack and pinion mechanism. And again, we went with Ackerman geometry because the vehicle wouldn't go at beyond a particular speed limit. Lastly, we saw the economical vehicles such as go-karts. In that, we used a throttling mechanism with Ackerman geometry, since it's simple in construction and economical in manufacturing. So that was all that we saw in yesterday's session. So I guess that was a quick overview. I would like to I would like to know if you have any doubts till now as to whatever we have learned in yesterday's session. Okay, so Abhinash is asking, the turning of knuckle axis is not same as the wheel yaw axis. Is there any advantage? Okay, so when you say yaw axis, you mean the when the wheel turns, it turns around some other axis to the knuckle, right? And I want to tell you that the wheel and the knuckle will turn around the same axle, same axis. It's called the steering axis, and it is defined by the caster and the kingpin inclination, which are terms that you might learn in your suspension books when you're studying suspension. And around that, the whole wheel will move, and the distance between the center of the wheel and that point of contact at which this axis will line up will be the scrub radius. This is something that is introduced again in suspension, which essentially tells you the difference between steering axis and the wheel center. Raja is asking what happens to the gyroscopic effect on different mechanisms on the geometry. So essentially, whenever you are, it's a very difficult topic to explain, but basically, whenever a tire is rotating, it's having a force in the perpendicular direction of the tire's face, right? And that's the gyroscopic force. And on different mechanisms, basically, it only affects if you are at higher speeds. So I don't think gyroscopic effect is like considerable in all of the applications. Okay, Raja is asking another question. That's a very good question. What happens when the pinion is at the end of the rack while turning the vehicle? Okay, so when the rack ends, right, at that point we have positive locks or positive stoppers which stop the pinion from rotating beyond a point. Okay, it might be as simple as a bolt attached to the casing which will stop the rack from moving side to side beyond the limit, or it can be something else which will basically stop the rotation or the motion of rack on the pinion, so that it does not go beyond the specified limit. Okay, Mahfuz Hashmi is asking why this anti-Ackerman geometry steering is used. Why this difference in angle is required in case of anti-Ackerman. Okay, so whenever the anti-Ackerman geometry is used, you need to have higher angle on the outer wheel than the inner angle, because, like I said yesterday, when there's lateral load transfer, you need to have the maximum angle on the wheel that is going to have the maximum load. Okay, and while you're turning at high speed, the maximum load happens to be on the outer wheel, so your outer wheel should be at higher turn angle. That's why we use the anti-Ackerman geometry. Okay, Yogita is asking, can't we use anti-Ackerman in all terrain vehicles? You can, but I don't think it will be very much efficient, because if you go with Ackerman geometry, that has its own advantage. Your wheel tear will be, or wear and tear will be less, the tires wear and tear will be less. It will be easier to calculate for your turning radius and all those things when you're making an ATV. If you use anti-Ackerman geometry in an ATV, the problem will be that the ATV does not go at a higher speed that it is supposed to generate the enough grip in the anti-Ackerman geometry. Also, another thing is, whenever you use anti-Ackerman geometry, what you see is you need to give a negative camber. Okay, negative camber to your wheels. So if you're seeing the wheels from the front view, this is how the wheels would look, front wheels. And when the load comes on the outer wheel, the wheel becomes straightened out. Okay, this one wheel will become straight. So that's the thing with anti-Ackerman geometry. But in Baha vehicles or in ATV vehicles, the displacement of the tire is very much. You cannot give negative camber. You have to give positive camber. And if you give positive camber, anti-Ackerman geometry cannot be applied. So that's why it is very difficult or not suggested to use anti-Ackerman geometry in your ATVs. Okay, Raja is asking why parallel geometry is not effective. Which aspect does it lack? So imagine we talked about the IC, right? Instantaneous center. So when we talk about IC, we are imagining a point around which the vehicle will turn, right? And if you consider a perfect rolling condition, in that case, in parallel geometry, the two lines coming from the front wheel will be parallel to each other. They'll never have a common intersection point. And that is why we cannot use parallel steering geometry for perfect steering. And if you use parallel steering geometry, the whole making of all the this thing, your components becomes a little bit difficult and impractical, to be frank. When you use parallel, it ultimately goes to the side of Ackerman geometry or anti-Ackerman geometry. So it's better that you go with anti-Ackerman geometry for applications where you don't want where you want to incorporate slip, and using Ackerman for where you don't want a slip happening. Mohit, the hydraulic steering is used in almost all commercial vehicles nowadays. Whenever someone says that they have a power steering, it means that they have a hydraulic power steering. Yes, anti-Ackerman geometry is not used in all vehicles because the lateral load transfer in all of the vehicles is not that much, and we want perfect rolling condition for commercial vehicles, mainly because you want to extend the life of your tires. So that's why we do not use anti-Ackerman in all of the vehicles. Okay, Vasu is asking how recirculating ball reduces the effort in heavy vehicles. Okay, so whenever we use a ball bearing, what we do essentially is reduce the friction between rotating components. And same thing happens in the rotating ball. We reduce the friction, and if you reduce the friction, automatically the human efforts get reduced. I'll take at least 2 more doubts. I'll try to solve at least 2 more doubts. Okay, to reduce the turning radius, right? So imagine when we say that we want to have a common intersection point, which is the instantaneous center, right? If we move the intersection point in, so for Ackerman geometry, it lied at the rear axle, right? And if you move it a little bit upwards and inwards, right, the turning radius would reduce. I'll show this one when we do the calculation for Ackerman geometry. You can better understand over there. But if the rear wheels are also turning, it will mean that the instantaneous center is much closer to the center of the vehicle, or the CG, and that's how it helps in reducing the turning radius. Okay, Bhushan is asking, can we use pneumatic system for steering? If yes, why? And if not, why not? Okay, so I guess you can, but I don't think it's much the hydraulic system is much more efficient because you can generate higher pressure with hydraulics when compared to pneumatics. Pneumatic can generate low pressure, and it does not give you that much amount of help when you're moving when you're reducing the steering effort. So that's why hydraulic is much more sensible to use. And Hiren is asking, can you explain camber caster in detail, please? Hiren, camber caster, I don't think we need for this session. That's why I'm not going to go over that. But essentially, if I have to say it, if I have to explain to you what camber is, if you see your vehicle from the front view, the tires would not be straight perpendicular to the ground. It will either be like this, both of them pointing inwards, or pointing outwards from the top, or both of them pointing inwards from the top, right? And that's the camber. At the same time, you can see the caster from the side view of the steering knuckle will never be upright. It will never be straight perpendicular to the ground. It will be tilted either to the front of the vehicle or to the rear of the vehicle, and that's the caster. So that's the caster camber. And one more thing, I guess you forgot to mention, was it toe. So when you see vehicle from the top view, if these two are the wheels you're seeing from the top view, these two will never point straight in the direction of motion. Okay, they will either be slightly inwards or slightly outwards depending on the application. So yeah, that's these three conditions that are used in suspension. Okay, so I guess that solves most of your doubts. I'm sorry if I cannot solve all the doubts, but yeah, I guess I've solved pretty much at least 80% of doubt. So I guess now I can move on to the next session, which is the calculation of your Ackerman steering geometry. Yeah. I'll start sharing my screen once again. Okay, so like I said, now we'll be doing the steering design calculation for Ackerman steering geometry. So in overview, what we'll study today is steps involved in steering design. Okay, so first step is going to be the Ackerman geometry calculation, where we'll calculate the turning radius and the outer wheel turning angle. We'll be focusing on these two things as our ultimate goal. Next, we'll be calculating the Ackerman arm. We'll be doing the Ackerman arm calculation, where we'll be calculating the Ackerman angle. And I'll tell you, we'll be assuming the length of Ackerman arm, but I'll tell you how to assume that and how to iterate your calculation with that. Next, we'll do the rack and pinion calculation, where we'll focus on the tie rod length calculation, pinion diameter and pinion teeth calculation, and similarly the rack calculations. And lastly, we'll move on to the steering effort calculation. So to begin with, there are a few assumptions we need to make in these calculations. Initially, we assume the inner wheel turning angle to be 40 degree. Now, why this is 40 degree? because various papers have been published and people have done research on this and practical experiments on this. Whenever you turn the wheel in a particular angle, and if it is going straight, 40 degree is something that the vehicle can follow. Okay, if it goes beyond 45 degree, it will incorporate high amount of slip and your turning wouldn't take place. So that's why we are assuming here to be the perfect rolling condition in the inner wheel, because maximum angle is going to be in the inner wheel. That's why we assume the inner wheel turning angle to be 40 degree, not 45. 45 is the limit, but we assume it to be 40 degree. Next, the Ackerman arm length. I'll talk about this more when we go for Ackerman arm length calculation, and that we are assuming to be 125 mm. And one more thing, if all of you can take a pen and a paper and note down all the things that are happening in this calculation, it will be very good for you. Solving the questions in your scholarship test also, and you can have notes for later reference, right? So Ackerman arm length again is 125 mm. The rack length, which is the length inside which is the outer limit of the rack, inside which the rack will be placed, right? So rack length is 420 mm. Again, I'll tell you why this is why this assumption is made when we go for rack calculation. Next, the rack axis distance from the front axle. So whenever we make a Ackerman geometry and rack and pinion mechanism, the rack is placed behind the front axle, okay, behind the imaginary center line that passes to the center of front two wheels, right? It is placed behind the front axle. So the distance between front axle and the rack center will be 200 mm. Okay. Next is steering ratio. Steering ratio is basically the ratio of how many degrees you have to turn to your on your steering wheel to get 1 degree turn in your road wheels. Okay, like I said, the steering wheel will be turning more than the road wheels to get more to reduce the steering effort, right? So when I say my steering ratio is 1:4, I mean that the road wheels are turning by 1 degree and the steering wheel is turning by 4 degrees. So that's what the steering ratio means. Next, we take the pinion module. So whenever we design any kind of gear, engineers have made this number module of pinion or spur gear module or something like that, which determines all the other values of this pinion. If you know one other value, if you know the diameter of pinion, you can figure out all the other values just using the pinion module. So that we are assuming that to be a 2.5, and it has no unit since it's a ratio. I'll tell you what pinion module is and everything when we go for pinion calculation. Okay, so to start with, we'll go to the Ackerman geometry calculation. So this is something that you had seen yesterday also. This is your inner wheel, this is your outer wheel. They both connect at a point which is called IC, and this IC lies on the rear axle. So imagine this to be the rear axle. So if this is the rear axle and these two are the front wheels, you'll have track width. Okay, the distance between two center points of two wheel is going to be track width. So that track width is 1400 mm. Okay, let's assume it to be 1400 mm. Next, the wheelbase, which is the distance between front wheel center and the rear wheel center, that is going to be 2200 mm. Okay. Next, this length extra in this figure, this length is unknown to us. Okay, where the IC meets on the rear axle, this length is unknown to us. So let's keep it as E. E is unknown. Next, we have the RO, which is the outside wheel turning radius that we have to find out, right? And then we have RI, which is the inside wheel turning radius for the inside wheel. Then comes the inside wheel turning angle, which in the previous slide I said that we are assuming it to be 40 degree, right? And then comes the outer wheel turning angle, which we'll call as phi. Okay, we don't know this angle what it will be, but we'll calculate these two things, the phi and the RO. Okay, so consider this red triangle over here. It is a right angle triangle, right? So we can use trigonometry. So first, to find the extra length E, right, we can use a formula tan theta. Tan theta is equal to wheelbase upon E. Okay, so this distance over here, this perpendicular line in this red triangle is the distance wheelbase, okay, which is 2200 mm, right? And this is the angle 40 degree. Theta is 40 degree. So we know tan 40 will be equal to 2200 by E. So with this, we can calculate E to be 2621.86 mm. Okay, 2621 mm in essence, right? So we have found out the length of this extra arm, which is connecting the IC. So IC is 2621 mm further away from the rear axle. Okay. Now, to calculate the Ri, so this length you have to calculate. Simply, we can apply Pythagoras theorem, because Ri is the hypotenuse and the base of this triangle is E, and the perpendicular of this triangle is going to be WB again. So using this, we can apply a Pythagoras theorem and calculate the Ri to be 3422 mm, right? And once that is done, Next, we go for the outside wheel turning angle. So again, this is where we want to, this is what we want to find out. So to calculate RO, the turning angle, the turning radius, outside wheel turning radius, we consider this green triangle. Okay, in this green triangle, again the vertical face or the perpendicular edge is going to be WB, and the base of this triangle is E plus the track width. So you can see here we have the track width, and if we add this E with the track width, you will get the base of this triangle, right? And using this, you can calculate, using this and a little bit of trigonometry, you can calculate what will be the RO. Okay, so this is the hypotenuse, right? This is the perpendicular side, and we know the base. Since we know the base and the perpendicular, we can calculate the hypotenuse using Pythagorean theorem, and that comes out to be 4,584 mm. Okay, now lastly, we need to calculate the outside wheel turning angle. Okay, this angle phi. To calculate this angle phi, we can use any kind of trigonometry you want. You can use sine also, cos also, and tan also, because we know all three sides of the triangle now, right? So you can use any of the relation. Here I have used sine. Sine phi will be equal to perpendicular upon the hypotenuse, right? So perpendicular here is going to be WB, which is 2200, and the hypotenuse is RO, which is 4584. So that comes out to be 28.67 degree. So with this, we have solved the Ackerman, we have done the Ackerman geometry calculation using simple trigonometry, just by figuring out, just by making this diagram in a way that we want it to be. So we want the IC to lie on the rear axle. We put the IC over there. We connect these two lines to the front wheel. We give this angle as 40 degree, this limited angle as 40 degree, right? So this angle was 40 degree. This was our first constraint. And apart from that, the only constraint we had was the track width and the wheelbase, right? So using this, we calculated all the other parameters of this geometry. So that concludes the Ackerman geometry calculation. Next, we have the Ackerman arm calculation. So when you go for Ackerman arm, so imagine this to be your layout of your vehicle, right? Let me just switch to the this pointer. This is better. So yeah, again we have the wheelbase, right? Just like the previous slide. We have the track width, right? Distance between the two side-by-side wheels. And if you cut the vehicle in half, you'll just need half of the track width. So if you cut the vehicle in half with this vertical blue line, right, you need the distance from this center would be TW by 2, correct? Now, consider this Z to be your rack, right? We have rack length we have assumed to be 420. Now, assuming this rack length is very important, because this will determine if the rack is going to stay within the vehicle or it's going to go beyond the vehicle. So if you're designing your vehicle, if it's an ATV or an student formula vehicle, it is preferred to keep the rack inside the vehicle at all times. So inside your chassis, the rack should be at all times whenever it's standing. It is preferred, but it should not be limited to that. If you need it to be outside at some point, it can be, right? So considering those parameters, we have assumed the rack length to be 420 mm because our track width is 1400 mm. Next, we have the Y over here, this line, this blue line, which is the tie rod. So this is something we have to calculate. We'll be calculating this in the next step. And we have the X, which is the Ackerman arm. So this arm is rigidly fixed to your wheel, right? And this arm is connected to the other end of the tie rod. So this is how the geometry works. So you have the rack which is connected to the tie rod at this point, and the other end of the tie rod is connected to the Ackerman arm. And this Ackerman arm, we are denoting it by X. Now we have assumed the X to be 125 mm. Why this? Why we have assumed it to be 125 mm? Because it should always be like it should. It is preferable to have this Ackerman arm in such a way, length of Ackerman arm in such a way that it does not cross the distance D. So if I move forward a little bit, this is a distance D, which is basically the distance between your rack and the front axis. So if the Ackerman arm length increases, it would go behind the rack. It should always be in front of the rack. It is preferred to keep it in front of the rack. In some cases, it is also in the behind the rack, but it is preferred to keep in front of the rack. So with that, I have assumed it to be 125 mm. Now, and also we have assumed this distance to be 200. So these are the few assumptions. These three assumptions, you can, like you can put different values, you can assume different values for these and run various calculations, run various iteration to find out what are the changes. So if you want, consider this as a task for you to write down all the formulas that we are using, write down all the steps that we are using, and for your understanding, what you can do is you can try changing one value. So here we have d as distance 200. Try changing this value to 250 or 225 or even 300 and see what happens, right? What would the final effect? And these are like these calculations I have done previously. That's why I'm showing you the final iteration. But initially we'll assume this, do the calculation, reiterate the process, and then come to a final product or final end of my design, right? Next, we know that the track width is 1400 mm and wheelbase is 2200 mm. So now consider this blue triangle. Okay, in this blue triangle, consider this angle to be beta. If you extend the X line, the Ackerman arm, on if you extend it behind, it should intersect the rear axle at the center. Okay, it should intersect the rear axle at the center. That's when we say that the Ackerman is 100%. Okay, so if I extend this behind till this point over here, this should be the angle it should make, right? This angle is beta. So how to calculate this angle beta, right? What we can do over here, if one more thing over here, if this point is below 100%, it will intersect somewhere around here. Okay, it will intersect somewhere around here. It will intersect the center of the vehicle somewhere around here. If it's above 100%, it will intersect the center of the vehicle somewhere around here. It will never be on the rear axle. If it's on the rear axle and on the center of the vehicle, this center line, this blue line, it is said to be 100% Ackerman. So for this calculation, we'll consider it to be 100% Ackerman, which means that it will have no understeer or no oversteer. If it's below 100%, the vehicle will understeer, which means if you turn by some angle, the vehicle will turn by lesser angle. It will not turn by that angle. And if it's oversteer, it means if you turn by some angle, the vehicle will turn by a little bit higher angle, not the angle that you have turned the vehicle into, right? So let's consider this to be 100% Ackerman. Now, to find beta, we can use this blue triangle, right? We know the base of that triangle is TW by 2. We know the height of that triangle is WB. And using trigonometry again, tan beta will be equal to half of TW, right? Which is 700, because TW was 1400, by WB, which is 2200. We can figure out the angle tan beta, the angle beta to be 17.65 degree. Right, and we can round this off to 17, because if I round it off to 18, let's say if I round it off to 18, this line will intersect somewhere around here, which will be below 100% Ackerman. And since I know I've done this calculation, again, this is a part of my iteration, I know that at the end of this calculation, the answer that the final product that I'm going to get is going to be understeer. So to compensate that, I can round it down so that this point will intersect somewhere around here. Okay, if I round it down from 17.65 to 17, this point will be intersecting the center of the vehicle somewhere around here, which will be slightly higher than the 100% Ackerman. Okay, so for that I'm rounding it down to be 17. Now, moving on to the tie rod calculation. So for tie rod, again, we'll be zooming in on the front section of your steering mechanism. Okay, you have your, once again, we have calculated this angle beta, which is represented in Z over here, this angle, right? We have X, which is your Ackerman arm, right? We have your Y, which is your tie rod, like we have seen in the previous slide, and Z, which is your rack. And then there's the distance D between the rack and the front axle. Okay, consider this horizontal line to be the front axle. And the whole length between these two sections or these two tires is the TW or track width. Now, if I take half section of this, if I draw a center line passing through, if I draw a line passing through the center of this section, this length will be TW by 2, because the whole thing was TW, right? So that will be half of track width. Now, just consider the left half of the image, okay, this part, just this part. In this part, consider this small triangle that is being made, okay, this dotted line and this hypotenuse. So it's a right angle triangle, and I'll just name them these sides M, N, and we know this side is Y, because Y is the tie rod, right? And we want to calculate the length of tie rod. So by simple geometry, I can say if I know the length of M and if I know the length of N, by Pythagoras theorem, I can calculate the length of Y. Excuse me. So what my aim becomes now to calculate the length of M and N. Okay, so calculate the length of M and N. I'll make another triangle over here, right? I'll make another triangle over here, this blue triangle, small triangle. Okay, and I'll name its sides as I and J. Okay, I'll name it I and J. Now, if I want to calculate the length I, Okay, what will be the formula for I? X cos beta. We know that this length from this point to this point is x. Okay, from this point to this point, it's x, right? So we can put that into this formula x, and cos beta is this angle. So using this, 125 cos 17 will be 119.53. So this is the distance I. Similarly, we can calculate this length, this j length, by using sine x sine beta. Again, x is this 125 mm, sine beta, beta is again 17 degree from this triangle, and j comes out to be 36 mm, 36.54 mm, right? Now, to calculate m, this is the important part, okay? Now, if you see the horizontal line, let me just take out the pen once again. If you see this horizontal line, okay, TW over here, right? It's addition of j, this part, addition of m, this part, and this part will be half of z, okay, because this whole thing is z, right? So this will be half of z. So I can say that z by 2 plus y plus j is t by 2. Okay, using this, the unknown we have is m, so we can calculate m is equal to half of tw by z, tw minus z minus j, that comes out to be 453 mm, right? And similarly, to calculate n, we can say n plus I is equal to d, because this is the whole length, right? So I know d, I have calculated I can simply calculate n. So using that, I have gotten the n value. Now once again, going back to our aim that we had previously, which is the value of y. We want to calculate the value of y. To calculate the value of y, again, we'll simply use Pythagoras theorem, where y is equal to under root m square plus n square, using Pythagoras theorem, right? And with that, we get the value of y to be 460.53 mm. Okay, so this is the tie rod length that we have gotten. Now with similar trigonometry, we can also calculate the rack travel for wheel turning angle of theta. Okay, and the formula for that would be this. Okay, I have just given out the formula because it's too complicated to explain this in this short time, but I keep this in front of you as a challenge to try it for yourself, to come up with this formula using the same trigonometry method that I have used to solve this y length, right? So you can use same kind of trigonometry. Your hint is, in this you will have to include the angle theta when you turn the vehicle, right? When you turn the tire. So theta will be 40, right? Beta is 17. The x value is 125, which we have used over here also. TW by z by 2, we know the TW by 2, we know z by 2. Since we know z, we can calculate z by 2 also. This term will be solved. We have recently calculated y over here, so we can write down y square minus, we have d, we know the distance d, we have assumed it to be 200. Again, x, we know cos theta plus beta will be 40 plus 17 once again, and this whole thing will be raised to 0.5, which means it's square rooted. Okay, so with that, we can calculate the rack travel, which comes out to be 56.7 mm, 56.07 mm. So this is how we can calculate the tie rod length and the rack travel calculation, distance. Okay, so after we have the rack travel, we need to do the pinion calculation. So for pinion calculation, I need you to understand how the pinion and rack work. Okay, so essentially pinion is just a circle. Imagine it to be a circle, and imagine the rack to be a straight line. Okay, now if I roll a circle out, it will open up into a straight line, right? It will open up into a straight line, and that straight line will be equal to the circumference of this circle, correct? If I take a circle, if I open it up like this, the length of the line will be the circumference of the circle. So that's why this line is 2 pi. Okay, 2 pi r, which is pi d basically. All right. So we know that this, in one rotation, the circumference, the distance traveled by the rack should be 1 times the circumference of the pinion, because pinion is a circle and rack is a straight line. If I roll the pinion on the rack perfectly, in one rotation, rack will move by pi d distance, or the circumference of the circle. So with this logic, we can calculate the pinion diameter. Okay, so now that we know rack travel for 40 degree wheel turn, right? We have calculated the rack travel in the previous slide 40 degree of wheel turn. And so what we can do, we can simply divide that 56.04 whatever we have, 56.07 rack travel that we have for 40 degree. We can divide that by 40 to get rack travel for 1 degree. Okay, and rack travel for 1 degree comes out to be 1.40. Okay, so imagine I take pinion and I take this section of the pinion, this angle. If I keep it to be, let me just get the pen once again. If I keep this angle to be 1 degree, okay, this angle to be 1 degree, this distance covered by the angle will be 1.4018. Okay, so 1 degree of pinion rotation will be 1.408 mm. Right? With this logic, what we can do, we want our steering ratio to be 1:4, correct? Which means for 1 degree of row turn, we should have rotation of pinion by 4 degrees, right? So instead of considering this to be 1 degree, what we will do, we'll consider this to be 4 degree. Okay, and what we will do, we'll consider, we'll say that 4 degree of angle is equal to 1.048, 1.4018 mm, and what will be 360 degree. Okay, what I'm doing simply 4 degree angle. If I take 4 degree angle, if I calculate the circumference of this circle or the length of this arc, that is going to be 1.4. What will be the circumference of the circle made by this arc? Okay, once again, what I'm doing, I'm taking a piece of circle. Okay, if you cut a slice of pizza, imagine if you cut a slice of the pizza which is 4 degree angle. Okay, and if you say that the pizza slice is of 4 degree in angle and the crust of the pizza, the arc length of the crust of the pizza is going to be 1.4 mm. So what would be the circumference of whole pizza, right? So that we can calculate by using this formula, which is given for arc length, which usually is written as S is equal to R omega, where S is the arc length, R is the radius, and omega is this angle, okay, which is at 4 degree. In our case, it will be delta 1 because we have the arc length as delta 1, right? So this is equal to this, right? We have R, which is unknown in both cases, and in our case, omega should be written in radian, right? It should be written in radian. So we multiply our 4 degree with pi by 180 to convert it into radian. And with that, we get the answer of the R to be 20.07 mm. And while designing a pinion or any kind of gear, you want to always work with round figure numbers. Okay, round numbers when it comes for your number of teeth, when it comes for your diameter of pinion, or when it comes for your module, you always want to work with round figure. And especially for diameter and number of teeth, it should always be an integer or a whole number. Okay, it should always be a whole number, definitely positive, and it should always be a whole number. Now we know that the radius is equal to 20.07 mm. And we can calculate the diameter, which is also the PCD of the pinion, pitch circle diameter. It is called, right? Diameter of pinion is called the pitch circle diameter, and that comes out to be 40 mm. If you round it down to 20, and if you double it, it comes out to be 40 mm. Moving on, we can calculate other pinion values. Since we know the module, we have assumed the module to be 2.5. Now I'll tell you why I assumed this module to be 2.5. Okay, since I know the diameter is 40 mm, the round whole number for my PCD is 40 mm. Module is essentially the ratio of PCD by number of teeth. Okay, module is equal to PCD by number of teeth, right? And number of teeth on pinion will be equal to PCD by module. Okay, so I have to divide 40 by some whole number to get another whole number. So I can use 1, I can use 2, I can use 2.5, I cannot use 3, right? And then again I can use 4 to get a whole number. Correct. So I've gone with 2.5. I can also use 2 if I want. And if I use 2, number of teeth will be 20. Okay. If I use 2.5, number of teeth you can see here is 16. If I use 4, number of teeth will be 10. If I use 1, number of teeth will be 40. Okay. So essentially these are various combinations that we have used. We can use, but I have selected it to be 2.5 because I wanted the number of teeth to be a whole number. And whenever you design a gear, any kind of gear, you always want the diameter or the PCD of that gear to be a whole number and the number of teeth of that gear to be a whole number. According to that only you can select the module. And the modules are defined in steps. Okay, they are defined in steps. There's 1, 1.5, 2, 2.5, 3, 3.5, 4, 5, 6, 7, and it goes on forever and ever. Like that, the module is defined, right? And for smaller gears, you can even find module which is 0.5, 0.75, 0.65 also. But for our case, I have assumed the module to be 2.5 because I wanted number of teeth to be a whole number, right? With that, I can calculate the addendum. So in this figure, you can see what addendum and addendum are. So if we consider this to be the pitch circle, okay, at which we calculate the pitch circle diameter. The gear will be a little bit above the pitch circle and little bit below the pitch circle. Always, this is the terminology of the gear, right? And how much ever it is above the pitch circle, it's called the addendum, and how much ever it is below the pitch circle, it is called the deadendum. Okay, and this addendum and addendum have empirical relations. So empirical relation, what I mean by empirical relation is they are in relation with the module. So if you select module as 2.5, addendum will be equal to 1m and addendum will be equal to 1.2m. So that with that, the addendum and addendum come out to be 2.5 and 3 respectively, right? Next thing is the working depth. Now, what is working depth? The working depth means that if you add these 2 points up, okay, addendum and addendum, you can see this distance between these two circles. Let me just clear the ink from this. So you can see the distance between this circle and the distance between this bottom circle, right? This will be addendum plus addendum, and that will be 3 plus 2.5, which will be 5.5. But whenever you mesh a gear with another gear, there will be some clearance, okay? There will be some clearance, and that clearance can be seen in this part, okay? This is the clearance circle, okay? And that clearance circle is because the top of the another teeth, okay, another gear, if you mesh this pinion with another pinion, the top surface, which is this surface, should not interact with the bottom surface. There should be some clearance between these two surfaces, and for that we have this clearance surface. And this clearance surface is given by defining the working depth, and working depth of the pinion is given by 2m. It is also empirical relation, and that's how we know the working depth is 5 mm. And this, if you add these two up, it will be 5.5, and the working depth is 5 mm. We can say the clearance circle and the clearance between this is 0.5 mm. So over here, it will be 0.5 mm. Okay. Next is the tooth depth. Okay. Now, when we talk about teeth depth or total depth, it is the addition of addendum plus addendum, like I said, right? So addition of addendum plus addendum, like I said, it is 5.5. If you remove the working depth, you get the clearance value. Now comes the difficult part, which is the thickness of the teeth. So thickness of the teeth is always calculated at the pitch circle. So over here, you can see this is called the tooth thickness, right? This length. And it is always calculated at the pitch circle. And the formula for that is pitch circle diameter multiplied by sine 90 by number of teeth. Okay. In our case, that comes out to be 3.92 mm. And this length over here, if I calculate this length from this line to this line, from this line to this line, that will be 3.9. And that's how we define the thickness of the teeth, each teeth. And lastly, we can define the circular pitch, which is important when we go for rack, because we need to keep the circular pitch and the module equal in rack and pinion for perfect meshing. Okay, so circular pitch is defined by pi m. You don't need diameter value over here. Circular pitch is simply pi multiplied by m. So we know value of pi is 3.4, and value of m we have assumed it to be 2.5. So that comes out to be 7.8 or 7.8539. Goes on forever and forever, because pi is a irrational number. And with that, we can conclude the pinion calculation and the values for different values for pinion. Next comes the rack design, right? Now, similar to our pinion, we have few terminologies in the rack. Now, we had calculated rack travel for one side. If you remember, it was 40 degree, which was 56.07 mm, right? Now, we need to calculate rack travel for both sides, because that was for one side. If you turn on one side, that much travel is required. But if you turn on the back to the center again, if you turn on the other side, right, that's the rack travel required on the both sides. So that can be calculated by multiplying the rack travel by 2. Okay, and that comes out to be 112.14 mm. Now, for perfect meshing of rack and pinion, the module of both should be same. So that's why the module of rack becomes 2.5 simply. Because we want to keep it, the meshing should be same. Now the actual pitch will also be same for the circular pitch of your pinion will also be same as the actual pitch of your rack. Okay, what is the actual pitch? Actual pitch is the distance between two consecutive points in the adjacent teeth. Okay, And in rack, it's a straight distance. It's not a circular distance, right? And this pitch is equal to pi m. This is the same as we took in the circular pitch in the pinion, right? And that is equal to 7.8539, similar to the pinion. Next comes is the number of teeth in the rack, right? So imagine now you know how much is the distance you require, right? How much distance you need to travel, and you know the distance between each consecutive teeth, right? So if you take this distance, right, this distance, which is your axial pitch, right, this one, and if you multiply it by number of teeth, okay, number of teeth, which is in this case tr, number of teeth on rack is tr. If you multiply this pitch by that, what you should get is total distance traveled, or total distance traveled on the rack, right? Using this logic, we can calculate number of teeth on rack, which is 2 delta upon pi m, and that comes out to be 14.27. Now again, you can see here the number of teeth on rack is coming out to be a decimal or a fractional number, right? And I want it to be a whole number. So for that, I will round this up to be 16 teeth with clearance. Okay, why I'm doing this? If I increase the number of teeth on rack, it is just going to increase in these direction, right? Horizontal direction. It is not going to affect my geometry anymore. And remember, what was the rack length we selected? The rack length we selected was 420 mm. Now, what happens is, imagine this to be the rack. Okay, I'm drawing it over here. This to be the rack. And in this, the teeth will be cut over here. Something like this, the teeth will be cut. Sorry for my bad drawing, but this is how it will be cut. This whole distance, right, from end to end was 420 mm. And this distance from here to here that we have calculated will be according to 16 teeth, right? So the actual length of rack becomes the TR, number of teeth, multiplied by pi multiplied by m, which is the actual pitch. Okay, so 7.85 multiplied by 16 will give us 125.66. So this length over here is 125.66. Okay, on the rack. So if I increase this length, even if I increase this length, all I have to do is cut extra teeth in this part. Okay, it will not affect my geometry at all. Okay, it will not affect my geometry at all. It will not affect my steering ratio at all. It will just increase the number of teeth over here. Now, you will also see I have written one more thing which says with clearance. So what I mean when I say with clearance, right? So sometimes what happens if I round it down to 14, let's say if I round this down to 14, right? Instead of 16, I round it down to 14. What will happen? The total distance on rack will be less than what is required. Okay, it will be less than 112. And I don't want that happening. So that's why I keep some amount of clearance above the required rack travel. And that's why we keep number of teeth as 16. And that's how we get this value of 125.66. So that's all about the rack calculation. Now we move on to the steering effort calculation, which is the last part of this section of today's session. And it starts with the considering assuming the weight of the vehicle to be 250 kg. One more thing that I would like to point out, all the numbers that I'm using in this calculation and also in the next calculation that I'll be using are considered randomly, and then I iterated those numbers and then found the answers which were logical. So these are not from some vehicle. I have not taken any case study. I have not done any specific. I'm not doing this for a specific vehicle. So for this calculation, all the numbers, consider them to be just a placeholder. You can put your numbers in these calculations, find out the result for your particular vehicle, right? Now, consider the weight of the vehicle to be 250 kg, right? And we say that weight distribution is 55% in the rear and 45% in the front, okay? Which means whenever a vehicle is made, all the load of the vehicle is not kept in the front, or all the load of the vehicle is not kept in the rear, and it is rarely divided into 50-50. There is some distribution happening. Okay, so let's assume that 45% of the load is happening on the front wheel, okay? Front wheels. Now, total weight on the front will be 45% of 250, correct? That comes out to be 112.5 kg. Now, the weight on one of the front wheel, this was on both front wheels, right? One of the front wheel will be this by 2, and that comes out to be 56.25 kg, right? Just one of the wheel. Now, if I think about it, force acting on the vehicle due to its weight or due to gravity, right? It will be the mass of that vehicle on each wheel. So this wheel has a mass of, this wheel is actually having a mass of 56 kg, let's say, right? 56.25 kg. So that will be multiplied by gravity to get me that vertical load that is acting on that particular wheel. And that comes out to be 551.81 Newton. And next thing, we can calculate the resisting force which is coming from the wheel when you're trying to turn. Okay, whenever you calculate your steering effort, it's calculated using assuming that the vehicle is stationary. Okay, because that's when the resistance is most. If you have ever driven a vehicle, you can say, or you know this, whenever the vehicle is stationary, it's difficult to turn your steering wheel compared to when the vehicle is running, right? So we calculate the steering effort for the worst condition, which is when the vehicle is stationary. And we need to calculate when the vehicle is stationary, what kind of resistance the wheel will be offering. That's what we need to calculate, right? So consider the coefficient of tire and road to be 1.4. It is never more than 1 in the commercial vehicle case, but in this case, I'm doing this for an off-road vehicle, or a vehicle which is going to go in the off-road condition, which is the worst condition once again. So that with that, the coefficient of friction between the road and the tire will be 1.4, right? I can say that the resisting force will be 1.4 times the W, okay, which was this. So if I multiply W by 1.4, this is the resisting force that the ground is offering to my wheel, okay, for turning. Now, I have the resisting force over here. There's one more term which comes in play, which is the scrub radius, okay. Scrub radius. Now, what is a scrub radius? If you imagine a tire, if you're seeing the tire from the front view, it should look like a triangle. It should look like a rectangle. Again, sorry for my crooked drawing. And imagine if you have a steering knuckle like this, okay, steering knuckle like this. If you have one point of wishbone over here, another point of wishbone over here, and the steering axis will be passing these through points, okay, through these 2 points. And wherever this axis touches the ground, the distance from that point, from the center point of the wheel, let me just erase this line. This should be the center line of the vehicle, of the wheel, okay, a straight line coming down from here, okay. The distance between these 2 points, okay, will be the scrub radius. Once again, if you see the wheel in the side front view, it will look like a rectangle, right? It will have 4 sides. And the steering knuckle, which is attached to the wheel rigidly, okay, this is attached to the wheel rigidly, is made in such a way that upper wishbone is attached over here, lower wishbone is attached over here, and the whole wheel will be turning about these 2 points, okay. So this becomes the steering axis in the front view. And if you extend the steering axis to the ground, okay, it will intersect the ground at some point, okay, this point it's intersecting, and the distance between that point and the central axis of your wheel is called the scrub radius, okay. So now whatever force was coming to my wheel is coming at this point, at the center of the wheel, okay. If I have to calculate the resisting torque, I have the force and I have the perpendicular distance. The perpendicular distance is scrub radius. So the resisting torque now becomes resisting force multiplied by scrub radius. And that in that I've assumed the scrub radius to be 25.4. Okay, you can the scrub radius is mostly assumed and then again iterated for suspension calculations, but for this calculation I've assumed it to be 25.4, and that the resisting torque comes out to be 19,622 Newton mm. Make note of this unit. I'm using Newton mm, not Newton meter. Okay. Now, once again, I'll give a quick overview of this. Initially, we considered that the weight of the vehicle was 250 kg, right? 55% of that weight was on the rear wheel, 45% of that weight was on the front wheel, right? So the weight on the front wheels becomes 45% of 250. That is 112 kg. And that was for the 2 front wheels. For one of the front wheel, it will be 56.25 kg, right? Now, this is the mass which is acting on the front wheel, one of the front wheel, right? I want to calculate the weight. So if I want to calculate weight from the mass, I'll simply multiply by the gravity, right? And that comes out to be 551.81 Newton. Okay, that's the load acting on the one of the front wheel. And with this load, I can calculate the resisting load that will be acting on my vehicle, okay, because of the coefficient of friction. So the coefficient of friction is 1.4. If I multiply this with W, it will give me a force which is high. This might be different if you're designing a commercial vehicle, if you're designing a racetrack vehicle. In that case, the coefficient of friction will be different. You'll have to refer research papers where they have defined the coefficient of friction through experimental methods, right? So for in this calculation, I've taken it to be 1.4. And with that, the resisting force comes out to be 772.53 Newton. And we then calculated the resisting torque, which is basically resisting force multiplied by the scrub radius. And I've already explained what scrub radius is. So we get the resisting torque to be this much, 19,622. Now moving on, we'll use this resisting torque to calculate the steering effort, right? Now, we have seen from the wheel side of view. Now coming from the human side of view. Okay, so now if I don't know why the diagram is not coming up. Yeah, so if I consider this diagram over here, okay, now consider this to be the tie rod. This is the tie rod. Okay, this blue line, if I'll mark it like a X. Okay, this blue line is a tie rod, and this is your Ackerman arm. Okay, and we have calculated this perpendicular distance, remember, I, which was x cos beta, if you remember, right? Beta angle was this, and we had calculated this distance I with x cos beta while calculating the tie rod length, and that is 190. So if I'm applying a force on the Ackerman arm, the tie rod is going to apply force in this direction, right? This direction the force is going to be applied, and if I calculate from this point, right, point of application of force and the perpendicular distance, I can get the torque which is applying over here, right? And this torque should be equal to my resisting torque. Okay, so to calculate the force on the Ackerman arm by tie rod, we'll consider distance I. P will be this force which is applied in this direction, right, from the tie rod. If I multiply P with I, I'll get the applied torque. Okay, this is the applied torque, and my applied torque should be equal to my resisting torque. Okay, that's implied. That should be at least as much as the resisting torque. So we know the resisting torque is 19,622, and we know the applied torque is P into I. So we know we don't know the value of P, we know the value of I. By inputting in this equation, we can equate the resisting torque, which is RF into square radius. We can equate that to P into I, which is your applied torque, right? And you can calculate the P. So minimum P should be 164 Newton. Minimum force applied from the tie rod to the steering knuckle should be 164 mm. Now, with that said, this is the force will be same which is applied on the pinion, because it is all rigidly connected, right? From the rack to the tie rod to the knuckle, it is all rigidly connected, and the pinion will apply the same amount of force on the rack. That's when the rack will apply the same amount of force on the Ackerman arm. Okay, so if at this point the load is 164 mm, 164 Newton, it means that the pinion is also applying the force of 164 Newton on the rack. Okay, so now going backwards again, we know that pinion should apply 164 Newton of force, right? So it will be same as the torque in the pinion should be same as the torque in the steering wheel, because they are rigidly connected, right? And we know pinion should apply 164 Newton of torque, 165 Newton of force, right? So what we can do is we can calculate the required torque at the steering wheel. And how we can do that? We can simply multiply this force, which is 164, by PCD by 2. What is PCD by 2? It is the radius of the pinion, right? And when we get the radius of the pinion, it becomes torque, right? Because we are getting the force and the perpendicular distance once again, right? And that torque comes out to be this one. And this is the exact same torque that we have to apply on the steering wheel. Okay, so this is the exact same torque we need on the steering wheel. Now consider the steering wheel to be of, let's say, some radius. Okay, so in this case, I guess I've taken 10 inches of radius. You can take any of the radius you have for your steering wheel, and you can apply. All you have to do, the steering effort finally comes out to be this torque divided by the radius of your steering wheel. Okay, this is in Newton mm, so you'll have to put that torque, radius into mm, and that comes out to be 25.94 Newton, right? So this is the amount of force you'll have to apply on your steering wheel to overcome the resistance that is offered by the ground. This is the minimum force that you need to apply, and it is well below the safety limits or the maximum limit of force that a human can apply. Okay, so once again, I'll just review this slide once again because it's a very important slide. Okay, to calculate the force applied by the Ackerman arm by the tie rod. Okay, so let's call that force P, right? What we can do, there's a force applied on this Ackerman arm from the tie rod, and we want it to be as much as we want the torque to be equal. We want the torque to be as much as resisting torque. Okay, so with that, what we can do, we can equate resisting torque with this torque. Okay, this torque is given by P multiplied by this I distance. We can equate this and calculate P. So this P is something which the rack is applying or the tie rod is applying on the Ackerman arm. If the tie rod is applying the force of P, rack is applying the force of P on tie rod. And if the rack is applying force of P on tie rod, the pinion is applying the same force on the rack, right? It's because it's all rigidly connected, right? Now, since we know what force is required at the pinion, what we can do is we can calculate the force required at the steering, because the torque of steering and pinion will be same. because they have same amount of rotation. They are rigidly connected. 1 degree of rotation of your steering wheel will be equal to 1 degree of rotation of your pinion, right? So that's why we can equate the torques of your steering wheel and your pinion. So pinion torque is equal to P multiplied by PCD by 2, right? Force into perpendicular distance, or the radius, is equal to torque, correct? That torque will be equal to steering effort multiplied by the steering wheel radius, and with that we can calculate the steering effort, which comes out to be, in our case, 25.94 Newton. And that's how you calculate the steering effort. So in review, what we learned today, first we did the Ackerman geometry calculation, in which we figure out the turning radius and the outer wheel turning angle. Then we went to the Ackerman arm calculation, where we calculated the Ackerman arm to be 17 degree and Ackerman angle to be 70 degree, and Ackerman arm length, I told you how to assume it according to the distance d. And then we did the rack and pinion calculation. Initially, we calculated the rack length to be 460, right? Then we got the rack travel, which was 56.07 mm. Then we calculated the PCD to be 40 mm. Once again, I told you that the PCD and the number of teeth should be whole numbers. Then we went to the rack calculation, where we calculated the rack length to be 125.66 and number of teeth on rack to be 16. And once that was done, in the end, we calculated the steering effort to be 25.94. So that's all for this section of today's session. Before I move on to the next session, which is going to be on this thing, Formula 1 F1 geometry, I'd like to answer a few of the questions. So please ask your questions in the chat session, and I'll try to answer them as soon as possible. I think it's going to take a few seconds since we've just started the doubts, and it'll reach to me. I'll try to answer as soon as possible. Okay, Bhavya, you're asking, is there a specific ratio for turning angles of inner wheel and outer wheel? There should not be, first of all. But for a particular geometry, you can have a calculation done for a particular type of geometry, and then if you want to replicate that, you can probably do that. But I don't think there will be a specific ratio. Sudarshan, you're asking why the Ackerman arm length should be lesser than D. So imagine if it's not lesser than D, the tie rods will be pointing downwards or rearwards towards the vehicle. And if that happens, it will the motion of the steering will not be smooth. It'll get stuck when you're turning your wheels. Okay, so that's why it should always be lesser than D. Okay, Mahefuz is asking, does module should be an even number? No, it should not be an even number. It's never like that. Modules are predefined by manufacturer and the engineers. So like I said, the range, it ranges from 0.2, maybe it starts from 0.2 and it goes beyond 10, 20. I don't know what's the upper limit, but you can find it in intervals like 1, 1.52, 2.53, 3.54, 5, 6, 7, and etc. Hussein is asking why calculation is done by rack travel and not by rack distance. What do you mean by rack distance? Can you please explain what it is? Like, I am not getting what rack distance actually is. Okay, Anirudh is asking very good question. What is the maximum steering effort a human can apply, right? So if you're punching someone, it's around 200 Newton, even more than that if it's a professional fighter. But if you're trying to turn your steering wheel, somewhere around 50 to 75 Newton. Okay, Omkar is asking what's the envelope of radius in the steering system. So, okay, whenever you're making a vehicle, right, and you have the outer wheel turning radius, right, and beyond the outer wheel turning radius, there's going to be the body of the vehicle, right? There's going to be the body of the vehicle, which is going to uncover some of the area when you're turning, right? That's going to capsulate some of the area when you're turning. If you figure out a circle, or if you figure out a shape in which your vehicle will be turning when you're turning, right? Your vehicle, the area which your vehicle will be occupying when you're turning, that area is called the envelope radius of your steering system. Okay, Shardul, when we say the inside wheel turning angle will turn 40 degree, the tire will turn less, right? When considering the slip angle. Okay, the tire will turn 40 degrees, okay, always, but the vehicle will not go in that direction if you consider the slip angle. Okay, Madhur is asking what's the optimum steering ratio for ATV? It's somewhere around 3 to 6. It should be sufficient. If you want to increase, you can also increase to reduce the steering ratio, steering effort. Raja is asking what happens to anti-Ackerman calculation. So that's what we'll do in the next session. I'll show you how to do the anti-Ackerman geometry calculation, and everything after that goes on the same way that it went for this thing, for Ackerman calculation. Bhumika is asking, sir, could you please explain tie rod calculation once again? Okay, tie rod calculation, let me just, at the end of this out session, I'll go back to those calculation. I'll do a revision on it. I'll share my screen once again. Okay, Fardeen wants me to explain the PCD once again. Okay, so you want to imagine there's a circle. If you open up that circle, right, it's a circle. If you turn it into a straight line, that line will have a length of pi d, the circumference of the circle, right? Now, whenever a pinion is rotated on a rack will be displaced, right, by some amount. And if the pinion is rotated by one whole rotation by 360 degree, the rack will move by some distance, right? So imagine my hand to be this rack and this to be the pinion, right? My fingers to be the pinion. So if I'm rotating my pinion, my hand will move horizontal direction. So if I move it 360 degree, what is the displacement of this rack? That's what I want to find out, right? So that is going to be always going to be the circumference of the PCD. And that is how we can, with that logic, we can calculate the PCD. Again, I'll revise this once again after a doubt session. Sahil is asking how different tires are able to get different velocities in supercar while turning. Is it only because of the differential? Different tires. I don't know about tires, but yeah, when you're turning, okay, when you're turning, your inner wheel and outer wheel should have different velocities, right? So if these two are the people and they are going around the circle, this person, which is in the shorter circle, which has a radius, shorter radius of the circle, will travel lesser than the outer person, and that's why this should move slower and this should move quicker. So this outer person or the outer wheel will be having more velocity, and this will be having low velocity, and that is what the differential does. Differential maintains the higher and the lower velocity in the inner and the outer wheel. Okay, in the calculation of steering effort, why the tie rod is not considered inclined? Hussein is asking a very good question. Hussein, you can consider the tie rod to be inclined, but all I was interested in was the perpendicular distance where the tie rod meets the Ackerman arm, right? So if you even want it to be inclined, the perpendicular distance is going to be same. So even if you use inclined tie rod, the perpendicular distance remains the same and your steering effort will come out the same. Okay, Bhaibhav is asking to do a quick recap on reasons for assumptions. Okay, I'll do that once again when we go to the assumption part. Yeah, Shardul has brought up a very good point. Shardul says that we did all the calculations on a planar geometry, right? We consider it to be a flat surface. But when we go into a vehicle, it's going to be a 3D geometry. What in that case? Correct. So all you have to do later on, right? And this nowadays is done by software. So all you have to do later on is apply trigonometry when you're, lifting up the rack, essentially. So imagine the Ackerman arms, they will both of the Ackerman arm will be in the same plane. Your rack will be on a parallel plane to your Ackerman arm always. So if this is the plane of your Ackerman arm, this will be the plane of your rack, and these two will be parallel to each other, right? And the only change that you need to make is the tie rod length. Okay, so simply what you will do, you will place these two on different planes on a software, and you can calculate the length of tie rod easily. Everything else remains the same, only the tie rod length changes in that case. Akash is asking what the minimum length of Ackerman arm. You can even keep it 50. It doesn't matter, as long as it satisfies your geometry. You can even keep it 25. But in most cases, it will not satisfy the geometry if it's too less. So it's preferable to keep somewhere around 100. Yeah, Suchetana Saha is asking a very good question. Why we consider the resistive torque of only one wheel? That's a very good question. Nobody asked it till now. I'm surprised. So when we calculated the steering effort, we calculated for one hand. Okay. So that's the steering effort you need to apply from one hand. If you put two hands, you can apply more effort, right? You can apply effort up to 200 and 300 Newton if you're using both hands. So if I calculate for one wheel, I can calculate the effort required by one hand, and that is definitely going to be more than what that is definitely going to be the less effort which I can apply with both my hands. So that's why we consider only one wheel. Okay, so Raj is asking what system or provision can be done to reduce the feedback from the ground. Okay, so at your tie rods and even at your rack, there are small compliant mechanisms added or suspension added, basically. So imagine having a spring in your tie rod, right? So whenever there's a bump, the tie rod does not transfer the motion directly. Some of it is absorbed into the suspension, and that's what the compliant mechanism steering do. Okay, Avinash is asking at high braking, load at front is high. So is the frictional modulus, so is the module of coefficient of friction, right? So this should be considered rather than the, okay. So what Avinash is saying, when you apply force, there's more load on the front and therefore the coefficient of friction will be maximum. Avinash, tell me, when you apply hard brake, can you turn your vehicle? So that's my question to you, because vehicle will be drifting in straight direction and you cannot turn the vehicle. So anyways, if you move your steering wheel, your vehicle will not be turning unless you have ABS. And if you have ABS, your vehicle will be in smaller motions and your effort will be still lesser than what it was when the vehicle was at rest. Yeah, Sudarshan is asking why can't we take the number of T to be 15? Yes, Sudarshan, we can take the number of T to be 15, but I took it as even numbers because if you divide the rack in two parts, okay, the pinion will be placed in the center at the initial position. It should be able to go in both direction equally. That's why I selected an even number. You can definitely select it as 15 also. Okay, Gauss Salim is asking what should be the caster angle. It should be positive or negative. So caster angle essentially should be positive for most applications, but there are some applications where negative caster angle is helpful. Okay, Kunal is asking what about the material and the diameter of various rods used in steering system. Okay, so this will for this you'll have to do some strength calculation and analysis, design analysis for this. And again, you can do the tensile and the compressive calculation for your tie rods, the shear calculations for your Ackerman arm, and with that you can calculate the diameter and the dimension and the material for these components. With that said, you will have to design it and test it in some simulation software so that you can be safe with some factor of safety. And even after that, maybe you want to do the practical test in it. Okay, Raja is asking why did we consider phi to be 17 degree? Okay, we consider b to be 17 degree, and what was this compensation made for? Correct. So beta was 17 degree. When I selected beta, when I calculated beta, it was slightly above 17 degrees, right? And I rounded it down to 17 degree. And with that, what happened? My Ackerman percentage went slightly above 100, and with that, I can be assured that even if tomorrow or even if further calculation there's some mistake, and if it goes under, if it goes into understeer, I can have some room to play because initially I have kept it oversteer. So that's why I like to keep in the initial stages at least. I like to keep my vehicle at oversteer. So that's why I selected it to be 17 degree. Vasu is asking what is the steering ratio of your F1 car. So Vasu, what do you think it should be? If the steering ratio of F1 car, Formula One vehicle, if the steering wheel can rotate only 90 degree, that's all. That's all they rotate. Okay, they do not rotate more than that, right? So quarter of a circle is what they rotate. So it is somewhere around 2, because if they want 40 degree or 45 degree of angle turn in their vehicle, and with only 90 degree in their hand, so steering ratio becomes 1:2. Yeah, Piyush, when Piyush is asking, won't we consider the weight of the tire while calculating steering effort? Yes, we will consider the weight of the tire while calculating the steering effort, and the weight that we considered 250 was including the weight of the tire. Cosmic Yeti is asking, does all vehicle from different company come with same steering ratio? No, in fact, same companies, different vehicle have different steering ratios. Swaraj is asking, can we have adjusting camber and caster while steering? No, in motion, it is very difficult to have adjustable camber and caster. Although there are some things you can do, mechanisms you can make, but it is never safe. Okay, Nilesh is asking, why did you select the load distribution of 45-55, why not 40-50? Okay, it is just an assumption. It's not a calculation. You can assume it to be 40-60 also, and you can calculate it for your own vehicle also. Jayesh is asking, why do we use bigger tires for tractor, for the back of the tractor? And that's a very good question, but it's out of the steering syllabus, but still I'll answer it. We want to have higher torque, okay, in the back of the tractor, and the rear wheels of the tractor is what gets the drive, right? And we want high amount of torque because it's going to go into places where it's difficult to get out. So that's why we have big diameter tires. Raja is asking, will there be any lag due to backlash? Definitely, there will be some lag because of the backlash in the rack and pinion. Shivam is asking, why can't we steer the vehicle when the wheels are locked due to heavy braking? So essentially, wheels are designed to rotate, right? They are designed to roll on the surface. If it slides when you're heavy braking, they will slide or they will drift on the surface of the road, right? And in that case, even if you turn the vehicle, they'll just drift in one direction. That's why you cannot steer them. So I guess that solves all of your doubts. Let me just move on to the next session, which is going to be on the Formula One and anti-geometry calculation. Okay, so moving on to the steering geometry design for Formula One vehicle. Okay, this is what we were waiting for. Now we have gone through the basics of steering. We have gone through the basic calculation of steering. Now we'll be doing a little bit more advanced calculation, and you can understand these calculations on the basis of the previous calculation. Okay, so we'll start the overview. In the beginning, we'll see what are the forces acting on a vehicle while it's turning. Okay, so what are the lateral forces acting on a vehicle while it's turning, and what are their effects? Then we'll understand what is slip angle and why it occurs. Okay, this is a very important part while calculating the anti-Ackerman steering geometry. And we'll see how the tire deformation occurs at a contact patch, and that's how it affects the slip angle also. Then we'll go for Ackerman geometry calculation. And like I said, we'll be going through the anti-Ackerman geometry calculation. We'll be going to the anti-Ackerman geometry calculation. And once you're done with the geometry, everything after that, the pinion calculation, the rack calculation, the tie rod calculation, the steering effort calculation, everything will remain same like we had in the previous session. Okay, so I will not be going over that once again. I'll just show you how to calculate the anti-Ackerman geometry. Okay, how to calculate the anti-Ackerman geometry, how to use simple trigonometry to calculate all the values in anti-Ackerman geometry. Then like I said, we'll do the calculation based on anti-Ackerman geometry. And lastly, I will talk about the placement and some of the features of the steering components in the Mercedes Formula One car. Okay, how they are placed, why they are placed in such a way, and what are the uses, what are the advantages other than the steering component. So I'll talk about these things at the end of the session. So moving on, what are the forces acting on a vehicle while cornering? Okay, so whenever you are in a vehicle and you're making a turn, you feel that you are moving towards the outside of the vehicle. Okay, you're moving towards the outside of the vehicle, and that is called the centrifugal force. So consider this to be the vehicle going on a curved track. Okay, again, let me just point out the laser pointer. Okay, so if you're going in like this, if you're sitting inside this vehicle, you'll feel a force in this direction. Okay, this will be the direction of force. You will move outwards. If you're turning, let's say if you're turning right, you'll move towards the left. Okay, that's how that's what you feel when your vehicle turns, and that's the centrifugal force. Okay, and that happens because of the lateral load transfer. So now there should be some force, right? Imagine, take a classic example. If I tell you about a box which is sliding down, which is kept on a surface, right? So all the forces are kept in balance. That's why it's not moving, right? Or let's keep a box which is still at a inclined surface and it's not sliding down. What it means is the frictional force between the block and that surface is enough to counteract the gravitational pull that the box has to slide down, right? So there's a force acting in downward direction in this direction, and it is being counteracted by the friction of the box and that inclined surface, right? So now, using the same example over here, you feel that force that you're moving, towards the outside of the turn, right? If you're turning left, you'll move towards right. If you're turning right, you'll move towards left, and that force is pushing your vehicle also away from the track. So if this is the track, if your vehicle is turning like this, it should go away from the track because that force is acting in this direction, right? But it does not go in that direction. So it means there's some other force acting to counteract the centrifugal force. Now, what is that force? That is a centripetal force acting in this direction. Okay, and that is counteracting the centrifugal force. Centrifugal force is because of the lateral load transfer. Centripetal force is to counteract that centrifugal force. That's the only purpose of that centripetal force. And that centripetal force will always happen at the tire, because tire is the only thing which is in contact with the road, right? Which is in contact with the road. Apart from that, nothing else will be affected by the centripetal force, right? Now, so as engineers, we have to design a vehicle in such a way while taking a turn, centrifugal force should never be more than centripetal force. If this happens, vehicle will tend to slide. So yesterday someone asked a question, how to drift. This is how you drift. You increase the centrifugal force and make it more than the centripetal force. Your vehicle will drift towards the side. So that's what it means. So if you're an engineer and if you want to make a perfect vehicle or good vehicle, you want your centrifugal force to be less than your centripetal force. Now, what happens to the tire contact patch? Okay, what is the tire contact patch first of all? So imagine on straight road driving condition or at a stationary condition, right? Imagine this bottom line to be the road and this is the side view. Okay, this tire will look like this in real life, but in reality it is deformed slightly over here at the point of contact. Okay, so essentially the contact patch, this is the top view. Okay, this is the top view you see on the right. The contact patch is not a straight line, but it is a 3D box. It is a 2D box. Okay, and because it's being compressed at the bottom, a lot of tires touching the ground. Okay, that's one thing. Another thing is because the tires are curved from the side. So if you see a tire, so this is the top view, you can see it is curved from the sides over here, right? These are the curves, and because it is curved from the sides, the contact patch becomes something like this. Okay, this is a slightly exaggerated version. It is not exactly like this, but it looks something like this. Okay, just for your illustration. Now, if I take this contact patch and see what happens in turning condition. Okay, now imagine if I turn this wheel around. Okay, if I turn this wheel around, it is going in a straight direction. Now you will notice that the road passing below the tire is not going exactly in the direction of the tire. Okay, they're slightly slipping. It's slightly slipping. So why is that happening? Okay, so this was the red axis or red line or red direction was the direction of the wheel by which the wheel is turning. Okay, direction by which the wheel is turning, right? The blue direction was where the road was passing by. Okay, and that was the vehicle's direction. That's where the vehicle is moving. And the angle between these two lines or these two directions is the slip angle. So again, we had this red line, which is the direction in which the wheel is pointing. Okay, and there's this blue line in which the vehicle is moving. Okay, so imagine my hand to be the wheel, and if I'm pointing the wheel in this direction and the vehicle is moving like this, right? If the vehicle is moving like this, if the vehicle is going straight, so the angle between the direction of the vehicle and the direction of the tire where the tire is pointed is called the slip angle. Okay, so now again, since this is going to be the outer wheel, let's assume this to be the outer wheel, and the centripetal force will be acting from outward to inward. So this will be the direction of your centripetal force. Okay, so now we'll see why this happens, why there's a slip in a vehicle, right? So what happens because of the centripetal force? There's a bulge in the contact patch. Okay, there's a bulge in the contact patch. The contact patch moves slightly from outward to inward side, and it looks something like this. Okay, and let's take an example why this happens. Okay, so imagine you are a particle on the tire. Okay, you are a particle on the tire or a thread on a tire. Okay, at this point, if this is the top view, this is the side view. This point is equal to this line. Okay, I'll do the animation. I'll show the animation, but remember this point is represented in side view by this line. Okay, now imagine the tire rotates and it approaches this contact patch. Okay, so initially it's approaching this contact patch. This point remains in straight line. It comes down in a straight line over here, right? Now, because it's in contact, it will go into while it goes into the contact patch. That's where the centripetal force is coming onto it, right? That's where the centripetal force is pushing it inwards, right? Because it's pushing it inwards, this point will now move in this direction. Okay, and the maximum centripetal force is not at the center of the wheel, it's slightly behind because the wheel is turning, remember, because the wheel is also turning. So that's why the maximum deflection will be seen over here, and that's why we get this bulge. So when it goes forward, it will come around like this from this bulge. So if you are a molecule on this tire, you'll essentially go around like this in straight line, come around like this in a straight line, follow this pattern out here, bulge out a little bit, and then go back to the original position or the original line. And once it leaves the contact patch, it goes straight behind because there's nothing else to do, right? And this repeats over and over again. This repeats over and over again. Okay, and just because you have the centripetal force and this bulge on the side, this is what is causing your slip angle. Okay, now slip angle is a very difficult concept. I guess I hope that you guys have understood this, how this moves. Once again, I'll show how this works. Okay, yeah. So imagine this to be the molecule on the tire, this to be one molecule on the tire, and that molecule is represented by a straight line in the side view. When the tire rotates, this molecule will approach the contact patch till here. Okay, it will go in a straight line. When it touches the contact patch, because there is a centripetal force acting in this direction, and one more thing I forgot to mention, and the tire is deformable, and the tire is elastic, right? It's made of rubber, so it will deform slightly, and this deformation is exaggerated. It won't deform this much, but it will deform slightly, and that's why it will be pushed towards the inner slide. And because the centripetal force will be maximum at this point, it will be pushed furthermore while coming behind. And once it leaves the contact patch, it will come back to its original position. Like I said, it's elastic, right? And this goes on forever and ever whenever the vehicle is moving and whenever it's turning. So this is what causes your slip angle. Okay. Now, moving on. So I hope you understand what the slip angle is. If not, I'll try to explain it once again in the doubt session. If not, you just write down that you have a doubt in a slip angle and be specific which part you didn't understand so that I can explain to you better. Now coming to the Ackerman geometry calculation. So if you see this diagram over here, you can see that the inner angle is higher than the outer angle. This is not Ackerman geometry. This is the anti-Ackerman geometry, right? So if I do this the opposite, now the outer angle is higher than the inner turning wheel angle, right? Now this becomes the anti-Ackerman geometry. And like we said, in the Ackerman geometry, the IC lies on the rear axle, right? On the rear axle, somewhere around here. But in anti-Ackerman geometry, IC lies somewhere around here. It does not lie on the rear axle. It will lie somewhere around here. Okay. So if I draw lines from this point to all four wheels, it will look like this. Okay. It will look like this. These are the four lines drawn to all four wheels, right? And this line is the radius by which this wheel will be moved. Okay. So now you will, what you may ask is, how is this happening, right? How is this happening? Why this tire is having this radius, right? It should have a radius which is perpendicular because it's a straight tire. It's not moving, right? But this happens because of the slip. Okay. So what is that slip now? So if I draw a perpendicular line at this point, if I draw a perpendicular line to this line, okay, I'll draw a perpendicular line at this point to this dotted line, and that will come out to be like this. And if I do that for all four wheels, that will be the direction at which the wheel will be traveling, at which all the wheels will be traveling. Okay, again, this might seem a little bit exaggerated, but I wanted to include this in the diagram. That's why I increased this angle. Okay, you might see that these angles are a little bit exaggerated, but in real life it's very less. So this angle between this red line and this thick black line is your slip angle. Okay, this wheel was supposed to move in this direction, but now it's moving in this direction. So this difference or this angle is called a slip angle. And you can see the least slip occurs in the outer front wheel, because that's where we know the maximum load transfer is going to happen, maximum grip is going to be happening, and that's why the least slip occurs in this wheel. Okay, so that's why I have denoted it almost zero slip. I've showed it as almost zero slip. It's not zero slip, but this is the least slip. Okay, so now once again, how we incorporate slip in here? So we have the anti-Ackerman geometry. We have outer wheel turning angle more than the inner wheel turning angle, right? And the IC will never lie on the rear axle. It will be somewhere around here. If I draw straight lines to all four wheels starting from the IC point, I'll get this lines, right? And if I draw a perpendicular line to this line at this point, at the point of intersection, at the point of the wheel center, I will get these red lines, right? These red lines is actually where all four wheels are moving. And the angle difference between this red line and this thick line is my slip angle. Okay, the actual motion of the wheels is this red lines, and the actual motion of the vehicle will be determined by this motion, right? By this direction, slip angle direction. Now, we can do similar kind of geometry once again. So if I divide this, if I draw a horizontal reference line which is passing through the IC, and this will be the angles, right? Again, we have the angles. Let's consider the front section of the vehicle now, for now. Okay, let's consider the front section of the vehicle. We have the track width. Let's consider this to be as 1400 mm. Okay, this extra length is again unknown, because this extra length is same as what you had in Ackerman geometry. It is unknown. Now the wheelbase of the vehicle is something else, right? The wheelbase is the whole vehicle, right? The wheelbase was in the whole vehicle from this point to this point, but now we are considering from this point to this point. So this is not the wheelbase, but let's call it apparent wheelbase. Okay, it's not called apparent wheelbase. I'm just naming it so that you can understand better. This is the apparent wheelbase. Okay, so this is unknown. We don't know what this is. Right now, what I need to do as a designer, I need to fix what my steering radius is going to be, or what my turning radius is going to be. So I fix the outer wheel turning radius. That maximum turning radius in my vehicle should be 5000 mm or 5 meter. I fix that. I want the maximum turning radius in my vehicle to be 5000 mm. Okay, and I will call these angles phi and theta once again, but this time theta will be the outside wheel turning angle and phi will be the inside wheel turning angle. Okay, that I'll do once again. Now, since the outside wheel is going to have maximum turning, right? Maximum turning, I want that to be limited. So I'm limiting it to be 40 degree. Okay, so including the slip angle, this is going to be 40 degree, right? And this angle, this 40 degree, is equal to the addition of or sum of the slip angle plus the angle by which the wheel is moving. Similarly, I'll mark this angle, angle phi, which is shown in green, for this wheel. And this angle is sum of the slip angle plus the angle by which the wheel is moving. Okay, so it's not the wheel turning angle, it's not the slip angle, it's the sum of slip angle plus this angle by which the wheel is moving, which is the angle phi. Now again, we'll do the trigonometric calculation to first calculate the apparent wheelbase, right? So apparent wheelbase can be calculated by the triangle, which is this one. Okay, the bigger triangle, right? From the bigger triangle, we can calculate the apparent wheelbase by sine 40. This angle sine 40 will be equal to apparent wheelbase upon hypotenuse. So perpendicular upon hypotenuse, right? And with that, we can calculate the apparent wheelbase to be 3214 mm. Right? So we calculated this apparent wheelbase with that. Next thing, we can calculate the extra length E. Right? So extra length E is equal to, in this triangle only, extra length E by Pythagoras theorem, RO square, which is the outside radius turning, this hypotenuse square, will be equal to AWB plus this length, which is TW plus E, right? So TW plus E square plus the AWB will be equal to 5000 square, right? And with this, we can calculate E to be 2430.17 mm. Okay, once again, this triangle is done. We'll move on to this smaller triangle, right? And in this triangle, now we'll calculate the inside wheel turning angle, So that can be calculated by tan of phi, which is this angle, this length by this length E, right? Because this length over here, this perpendicular over here, will be equal to this perpendicular over here, which is AWB. So AWB by E will give you tan of this angle, and that angle comes out to be 52.9 degree. So if you think about it, phi in this case will be greater than theta. Okay, inside wheel will be turning, or inside wheel will be having motion at an angle more than the outside wheel, but the inside wheel is turning by lesser degree. So like I said, it's the phi is not the turning angle of this inside wheel, it's the sum of slip angle plus inside wheel angle. Okay, so this is how the Ackerman geometry calculation works, right? The whole Ackerman geometry calculation. After this, what they do, they have tire data, okay, which is very confidential, we cannot get our hands on to that, but they have the tire data on different loads at different speeds at different turning angles. Okay, and that tire data is nowadays computerized. You just get a software by Pirelli if it's a Formula 1 race, and they give you these parameters. Okay, they give you the input parameters. You can put in the speed, you can put in the mass, you can put in the angle by which you want to turn, and it will output the slip angle for each of the wheels, right? And if you have the slip angle for each of the wheels, right, all four wheels, and if you have the angle over here with theta phi, right, you can calculate by how much you want to turn your wheel actually, right? Once you have that, you can easily go on to your calculation for your steering, the rack travel, pinion, and similar to what we did in the Ackerman geometry calculation. And this is why I wanted to take you through the Ackerman geometry calculation first, so that this part is only the difference between that and this calculation, right? So once you are done with this part, you know these two angles, you know the outer turning radius, you calculate these things by trigonometry. Same thing you'll do for the bottom part of the vehicle. So if I go back and show you the bottom part of the vehicle, you can do the same over here. You can make this big triangle, you can make this smaller triangle, right? And you know this angle, you know this angle, you know this length, you know AWB, you know the AWB, you know the overall wheelbase, you can calculate this length, right? You know the distance E. With that, you can calculate these angles also. And once you know these angles, and with the software that the tire data provides, right? With the provided tire data, you can calculate what would be the slip angle for each of the wheel. Once you know that, the slip angle for the rear wheels, by the way, is going to be whatever angle you calculate over here, right? Because the wheels are not going to turn; they are going to be at 0 degree angle, right? Rear wheels, but they are going to follow this path, this red line path. So whatever angle you calculate at this point, right? These angles. So let me just mark it with some color. Let's say I'll just select one yellow color over here, right? And let me see a blue color maybe for this angle. So this blue angle, right, will be the slip angle for rear right wheel or rear outer wheel. Okay, let me just go back to the laser pointer. So this blue angle will be the slip angle for rear outer wheel. This yellow angle will be the slip angle for rear inner wheel, right? And in the front, what happens is this red angle is the sum of slip angle and the turning angle of your outer wheel. This green angle is the sum of slip angle plus the turning angle of your inner wheel. Okay, so that's how it works. Once you go through with this, you can calculate the slip angle, and that's how you can move on with the calculation, what we did in the previous calculation. So I hope this is very much clear, because all we have to do is calculate this differently, calculate the geometry differently, and just figure out what the slip angle will be. Calculating the slip angle is a difficult process, and nowadays it is done by just softwares. So that's why I cannot show you, because it's the confidential data. They do not provide the data easily, so I cannot show you what the slip angles for each of the wheel will be. But once you know the slip angle, you can easily calculate how much degree your wheel should be turning if you're designing a Formula 1 race car, right? And with that, you can do the calculation that we did in the previous section. Now, moving on to the components in the Formula 1 steering system, okay? So there are a few things that I wanted to point out in these things, right? So you can see in the first image, this is the rack and the pinion. You can see the rack and the pinion actually have helical teeth. This is what we call a helical teeth. They are at an angle, right? And they are completely made of carbon fiber. Okay, both the components are completely made of carbon fiber. There are two reasons for that. They want to reduce the steering weight, and they have put helical to avoid that backlash. Remember, I told you about the backlash. To maintain a constant contact, people also use helical gears. It's also very much efficient to use helical gears to avoid the backlash, right? You will see there's a spline shaft over here, right? And there's a hole over here, right? if you come to this figure, you can see the pinion over here in this part. Okay, this is the pinion, and at the end there's going to be a ball bearing which fits in this hole. Okay, that part is over here, and this spline shaft is connected to your steering column, which is over here, right? And in this spline shaft, there's going to be an electric motor which will help the steering, which will help in reducing the steering effort. Okay, so essentially what is happening, we have our pinion, we have our rack, we have a hole over here which is going to be connected to a bearing which will help it rotate properly, right? The other end is going to be connected to a spline shaft. Right? This is the spline shaft. It is going to be connected to a spline joint, and that is then in turn going to be connected to a UJ or universal joint. There are two UJs in Formula One race cars. This is the first one. Let me just mark that one in red. So this is the first universal joint, and this is the second universal joint. And between these two universal joints, there's a motor. You can see this as the motor, and this motor is attached to the reduction gear, and this will help, reduction in reduction of your steering effort. Okay, like we studied yesterday, the electric, fully electric steering system, right? That's how this motor is going to help in rotation of this arm, this column, steering column. And this in turn, this UJ is in turn connected to your steering column. So this here is the steering column, which is going to be connected to your steering wheel. Okay, so driver is going to be connected with this this column over here. And one more thing I want to point out is this thing, this white patch you can see in this part, right? So this is actually the side view of your rack. Okay, and initially whenever you imagine rack and pinion, right, whenever you imagine a rack and pinion, you imagine it to be rack to be in bottom and pinion to be on top, right? You imagine the rack to be like this and pinion to be on top. But in Formula One, it's upside down. The rack is on the top and the pinion is in the bottom. Now, why this is done? Because if you put it below over here, and if you use like that in anti-Ackerman geometry, if you turn left, your rack will move towards. If you turn right, I'm sorry, if you turn left, your rack will move towards right, and it will push your wheel in such a way in anti-Ackerman geometry that the wheels move in right direction. So essentially, you're moving left, but your wheels will be moving right. Right? If you put the rack in the bottom in anti-Ackerman geometry, if it's Ackerman geometry, it's best to use rack and pinion on top of it. In anti-Ackerman geometry, rack comes on top. Okay, and in this way, we can ensure whenever we turn left in the steering wheel, the road wheels will also turn left. And that's one more thing that I wanted to point out. Apart from that, there are a few components. If you are interested, this here will be the braking master cylinder overall, this part, right? And then we have the clutches and we have the clutches and the accelerator parts, which are helping in moving the components. And then there's this brake fluid master cylinder, which is going to help brake fluid reservoir, which is going to help in braking system. And all these things work inside the cockpit, inside the Formula One vehicle. So this is how it looks if you take a cross section. And that's it for the inner part of the Formula One. Now, talking about the external part. So you see, in this picture, you'll see the push rod. So this is the push rod which is connected to the suspension. I'll just name it PR, push rod. And this is the upper wishbone, right? So upper wishbone, which is connected to your suspension. And somewhere around here, I don't know if you can see, but this right here is your lower wishbone. Okay, so lower wishbone. So this rod over here. And from this point, you'll see there's a rod coming out, and this is your tie rod. Okay, this is your tie rod, this part. And you'll see all of them are made in such a way that they have a cross section of an aerodynamic wing. Okay, so this cross section is kind of similar to this cross section over here. And in this pic also, you can see clearly that wherever they are coming out in such a way that they are aerodynamically enhanced. Now, why they do this? Because if we use round pipes, just like we use in a commercial vehicle or any of the vehicle that we make, in that case, they will be generating high amount of drag. And we don't want drag to be coming on your Formula One vehicle. That's why these are made aerodynamically. The cross section of this will be like a wing, like a downforce wing or inverted wing, right? And this will be actually, these rods will actually be generating downforce as they are moving forward, right? So that's the whole purpose for making these rods in that way. Okay, so once again, the cross section will look in this way, and they make it in carbon fiber again to make it light. So that's all for the Ackerman geometry calculation and components for steering system. And one more thing, okay, in this pic you can actually see the push rod and the tie rod differently. Okay, so here's your push rod, this part is your push rod, this is your upper wishbone. Okay, this is the push rod once again. Okay, this is the upper wishbone, and this right here, this part is the lower wishbone, and this rod is just coming out. It is your tie rod. And over here you can see the cross section of these rods, right? They are flattened. Okay, they are flattened to be more aerodynamic. So that's all I wanted to talk about these things. And in review, what we learned in this session, in this section, was what are the forces acting on a vehicle, which are centrifugal force and the centripetal force. We studied that the centrifugal force was happening because of the lateral load transfer. Centripetal force was happening to overcome the centrifugal force or resist the centrifugal force, right? Next, we understood what is the brush model. So what we studied the slip angle and how it occurs, the tire patch model. It is also known as the brush model because we assume the tire to be like a brush, like the brush, the hair of the brush are so smooth and so flexible. That's what we assume the tires thread to be, and that's why it's called a brush model, right? Next, we saw how the deformation in tire contact patch happens, right? Next, we did the Ackerman geometry calculation, and lastly, in the calculation we saw the inner and the outer wheel turning angles, how we can arrange that and how we can incorporate slip into that. And lastly, I went through some placement and features of the steering components in Mercedes Formula One car. So that's it for this video. I'm sorry, that's it for this session. I'll just do one thing. I'll revise the previous session and this session very quickly before going to doubts. So hold your doubts for now, because I want to be thorough. I want you to be, gone through once more. I wanted to all of you to go through all this session once more, and then we'll ask the doubt. So let me just go through both of these sessions quickly. Okay, so I'll just start from here. So initially what we did the Ackerman geometry calculation, in which we did calculated turning radius and the outer wheel turning angle, right? Then we went for Ackerman arm, where we calculated the Ackerman angle basically, and I told you why we should have the Ackerman length less than D. Next, we did the rack and pinion calculation, in which we basically did tie rod calculation, pinion calculation, and rack calculation. And lastly, we went to the steering effort calculation. Again, going through the assumptions, someone has asked me to go through the assumption once again and the reasons for choosing these assumptions, right? So inner wheel turning angle was kept at 40 degrees. Why 40 degree? Because whenever you turn a vehicle, whenever you turn your wheel, and if it's more than 45 degree, the turning won't happen, it will slip. It will go into sliding, okay? It won't follow that perfect rolling. So that's why, to avoid that from happening, we are assuming it to be at 40 degree, not taking it to 45 degree. Okay. Next, Ackerman arm length. So it should always be, so if I draw this diagram, okay, if I draw a straight line, which is going to be your front axle, right? This is going to be your rack, okay? And from here, you have, they're going to be, okay, this is going to be the distance D, the rack and the front axle, right? This is going to be the distance D. If you have, from this point, if you have your Ackerman arm, which is passing behind the rack, okay, the tie rod will be faced like this. So this will be your tie rod, or Y. Let's call it Y because we are familiar with Y. So this will be Y. And imagine if you push this in this way, if you push this in this direction, what will happen? This tie rod will tend to move, it will tend to become straighter. It will be like this, right? It won't be pushing the Ackerman arm so much, it will just become straight, okay, if the resistance is too much. So that's why we try to keep it in this way. We keep the Ackerman arm this way, the tie rod in this angle, and rack over here. So again, rack over here. So this will be your Y. And if you try to push this, since all the load is going in this direction, you can have this turning proper. So that's why we want to keep X less than D. Okay, so that's why we keep Ackerman arm length 125. So I hope that clears the doubt. Someone has asked this doubt also. Next, we assume the rack length to be 450 mm. So like I said, the rack was like this, right? The rack was like this, and inside that we had the teeth. Okay, inside that we had the teeth which went like this. So this actual length, we later calculated how much this would be. But at the points where the tie rod will be attached, the distance between those points, we assume to be 420 mm. Okay, the distance between these 2 points, we assume these to be 420 mm, and this we later calculate to be 125 point something, I guess 66 mm, which we calculated later on. So the distance between 2 points where the tie rods will be attached was 220 mm. Next, we assume the rack axis distance from the front axle, right? So again, going back to that diagram, which looks something like this, right? This was the rack, and here was your front axle. So this distance was d, right, which is 200 mm. So what you can do, like I said, you can iterate your calculations. You can change this assumptions. You can make it 250. I'm sorry, you can make it 250. You can make it 150, whatever you like, and try to do this calculation again and again. And you'll find out whatever changes, what are the changes that you're getting, what are the turning radius you're getting, and optimally you have to select this rack axis distance. So for this calculation, I felt like 200 is the most proper one. If you want to try out, you can try out few different variations of this 200 mm. Next, we went to the steering ratio. What was the steering ratio? Steering ratio is the ratio between the angle turned by your wheel to the angle turned by your steering wheel. Okay, the angle turned by your road wheel to the angle turned by your steering wheel. So if you rotate your steering wheel by 4 degree, okay, that's when 1 degree of your road wheel will be changing. So that's what steering ratio means. And lastly, we saw the pinion module. Like I said, pinion module come in the standard. So it's 2, 2.5, 3, 3.5, 1, 1.5, and so on and so forth. But for all calculation, I wanted the PCD and number of teeth to be a whole number. That's why I selected this module. Okay, next thing we did, we went to Ackerman Geometry calculation, where we knew the track width and the wheelbase and this extra length E. With some trigonometry, we calculated these values. With the red triangle, we calculated E using tan. And similarly, we calculated the inside turning radius using Pythagoras theorem. Next, we went to this green triangle where we calculated the RO with Pythagoras theorem. And once we have all three side knowns, we can easily calculate the green angle, which is angle phi. So with this, we had calculated all the things in the Ackerman geometry calculation in our first session. Next, we went to Ackerman arm calculation. Now, most of you had a doubt in this. What I essentially did was I extended this line. Okay, I extended this line in such a way that it should intersect the center line of the vehicle. Okay, this is the center line of the vehicle. Let's call it C. The center line of the vehicle at the center of rear axle. So this point it should intersect. So what should be this angle? That's all I did. That's all I calculated. Okay. So now that angle came out to be in this blue triangle. Remember, we took this blue triangle. That angle came out to be 17.65 degree. Okay. So essentially, at this point, it should be 17.65 degree. But what I did, I rounded it down to 17, right? So I decreased this angle, right? I decreased this angle. So this point essentially went somewhere around here, okay? And I know that is going to go a slightly like 100 point, let's say 2%. That's all the difference was, right? And why I did this? Because I know when I design this kind of vehicle by these numbers, I have did this calculation. So because I know in this calculation, at the end, it's going to go into understeer. So it's good to have some amount of compensation with this angle, with this Ackerman percentage. There are multiple ways to calculate the Ackerman percentage, but I never see a point in calculating the Ackerman percentage. That's why I never teach one. But if you want, you can calculate the Ackerman percentage. There are multiple formulas that you can find on the internet, which are very easy to, do. But there's no point in calculating that. It does not give you any engineering ideas for your design. So that's why we didn't get into that. Now, like I said, we kept it a little bit over 100%. That's why we assumed the beta to be 17 degree. Next, we went for tie rod calculation. In tie rod calculation, we knew this angle was beta. We know x, y, and z, right? We know x. We had to calculate y. We knew z, and we knew the distance d. And we know that track width and half of the track width, since we are considering only the half of the image. And with this, we generated the smaller right angle triangle over here. Let me get back the laser once again. Yeah, we consider this triangle over here with sides m, n, and y. With Pythagoras theorem, if we use Pythagoras theorem, we can calculate y by if we know the length of m and n, right? So to calculate m and n, we calculated two more distances, which was I and j, and we did that by using this blue triangle, which was x cos beta and j sin beta, which came out to be these values. And then using simple logic, j plus m plus z by 2 will be equal to t by 2. With that, we calculated m. And another simple logic, n plus I is equal to d, right? With that, we calculated the distance n. And once we knew these two distances, by simply putting it into the Pythagoras theorem, we found out the value of y, which is 460 mm. And I told you with similar calculation, you can do the rack travel calculations also. With similar trigonometry, you can do the rack travel calculations also. And this is something I'm leaving you guys to try this on. Okay, you give it a try. And if you can't, you can just message me on LinkedIn. I'll try to help you. But it is very simple. Just like we did in this trigonometry, you just include the turning angle of each wheel. That's it. That's all you have to do. And then you can find out these values also. Now, then we went for the pinion calculation. Like I said, if you open up a circle, it will be a straight line, and that length of the line will be 2 pi, pi d. And essentially, if it's pi d, it means it's the circumference of the circle. And with that, we said that if the rack is rotating by one whole rotation, the rack travel should be same as pi d, or the circumference of the circle. And using this logic, what we did, we knew the rack travel for 40 degree. We calculated it for 1 degree. 1 degree of wheel turn, right? 1 degree of wheel turn. We calculated the rack travel for 1 degree of wheel turn, and we then said, what would it be if we like this rack travel should be equal to pinion's 4 degree. And if pinion is at 4 degree, rack travel is equal to the circumference of the pinion. It means for 1 degree of rack travel, we should have 4 degree turn in the pinion. So 4 degree of turn will be this distance. Okay, this distance. And with that, using the formula for arc length, we calculated the pinion diameter, okay, which came out to be 40 mm. And then with this, we used the module and some empirical values, and we calculated the values for pinion, which came out to be the module, pinion PCD, number of teeth, which is basically PCD upon module, since module is the ratio of PCD and number of teeth. And then we decided we calculated the addendum working depth, total depth, and the thickness of the teeth by using the empirical values. Similarly, we went to rack travel calculation. And in rack travel, like I said, initially we calculated for one side rack travel, and then we went to two-sided rack travel, which came out to be double of what we had initially calculated. And then we took the same module for pinion and rack. We calculated the actual pitch and number of teeth, and then we rounded off to a higher number to get it with clearance. And then we found out what's the actual length of the rack. So that came out to be 125.66. Lastly, we went to steering effort calculation, where we took the load of the vehicle on one tire. We multiplied it by the gravity to get the load in Newton. We multiplied that load with the coefficient of friction to get the resistance force. We multiplied this resistance force with the scrub radius to get the resisting torque. And we want to overcome this resisting torque, right? So we overcame that resisting torque by equating that resisting torque with this torque, which was P multiplied by this perpendicular distance I, right? And someone was saying, why did I consider this tie rod to be straight, right? This tie rod to be straight. You can consider this to be inclined also. It doesn't matter. Ultimately, you want a perpendicular distance from this point to this line, right? So ultimately, you'll get this line only. That's why I used a straight line over here. So the tie rod is actually this one, but this is just a representation of the tie rod, which will give this perpendicular distance like this, right? And equating those, we found out the value P. Now this is the P that the pinion is applying. So we can equate this force onto pinion. And we know that since the rack and pinion are rigidly connected, the pinion should be having the same torque as your steering wheel. So we can apply the same torque on the steering wheel. And with that, we can calculate the pinion at the torque at the pinion, which was this, right? Which was, let me get the laser pointer once again. Yeah, which was this, P multiplied by PCD by 2. This was the torque at the pinion. Then we this same torque will be given to the steering wheel, and we divide that torque with the steering wheel radius, and we get the steering effort. That's how we calculated the steering effort, right? Next, I'll just go through the Ackerman geometry anti-Ackerman geometry once again. So initially we saw there are two forces acting on a vehicle while turning. One is the centrifugal force, and to counteract it, we have the centripetal force. And the centrifugal force is generated due to lateral load transfer, and the centripetal force is generated to counteract the centrifugal force. And as engineers, it is our job to keep the centrifugal force lesser than the centripetal force, right? Then we studied how the contact patch acts on a straight driving condition where it's on straight road. It looks something like this egg-like shape. And when you're turning, it deforms slightly because of the centripetal force, and it looks like this, and that's what generates your slip angle, right? And with we also saw the animation where if a molecule, or if you put put hair of brushes on a tire, one of that hair will move in this way. Okay, that's what the brush model means, and that's how we saw how the motion of this particle will be, and that gave us an idea of how the slip angle is created, right? And this goes on forever and ever whenever you're turning, right? And we used this idea to we understood this idea, and then we went for the geometry calculation. In Ackerman geometry, outer wheel turning angle is higher than the inner wheel turning angle. Right, IC is somewhere around here, which is not at the rear axle. We connected IC with all four wheels. We drew perpendicular lines from this dotted line at the center point of each wheel, right? And we got the direction in which the vehicle is moving for each wheel, right? The direction in which each wheel is moving, and the difference between the angle, or the angle between this red line and this black line, is our slip angle, right? Then we considered the upper half of the front half of the vehicle, right? We calculated using trigonometry some of these parameters, which was AWB, the length E, the angle phi, and these angles were actually this phi angle is the slip angle plus the angle by which the wheel has turned, right? Similarly, this theta angle is equal to slip angle at this wheel plus the angle by which this wheel has turned. But in the rear wheel, since the wheels are not turning, whatever angle you get at this lower section over here will be the slip angle. Then we talked about some of the components used in Formula One steering system, how they look, why they are made in such a way, right? Which included the pinion, the rack, how they are arranged, how they are compact, how they are placed in this compact spot, right? And then we also saw what is the cross-sectional shape of the tie rod and the suspension arms to make it more aerodynamic. And they are made of carbon fiber to make this complicated shapes and to reduce the weight on the vehicle. So that's what we saw into this session, and I would now like to answer the doubts. If you can now post the doubts, I guess. Kiran is saying in anti-Ackerman, the slip in the inner wheel should be 0. Technically, yes, the inner wheel will be suffering from 0 slip, but at the same time, the contact patch of that inner wheel is so less that it will move essentially in the air. So that's why the slip is higher, the slip angle is higher, but it is suffering from very less slip. You're absolutely right, because it has no load, it has no grip. The slip angle is very less. The actual slip happening in the wheel is very less, but the slip angle is higher in the inner wheel. Vasu is asking why we need more slip angle on the loaded tires. No, we do not need more slip on the loaded tires. We need less slip on the loaded tires so that we can get maximum grip in the direction we want to turn in. Prashank is asking how is contact patch of the tire responsible for affecting the slip angle of the tire. So see, contact patch changes when the centripetal force is acting on it, and because of that centripetal force, some of the tire threads will move in one direction, right? They'll move inside, and if you draw a tangent line to that profile, okay, the profile that was made by the contact patch, that's the direction your vehicle would go in, and that's why the contact patch creates the slip angle. Okay, Shritam is asking, sir, my doubt is the tack width is considered or the pivot distance considered in calculation of steering geometry. Correct. When you calculate your steering geometry, you always consider the pivot distance, which is your distance of your steering axis on both of the front wheel, right? But for initial calculation, it's better to consider your track width only, and then do the calculation. And later on, when you go for more precise calculation, while before manufacturing, when all the suspension systems are done, all the angles are defined, and everything is done, at that time you can take the pivot distance. Kazi is asking, are these assumptions for common for all types of car design? No, these assumptions are just for this calculation. You will have to make your own assumptions. You'll have to do your own research for different types of car that you're making, and accordingly you can do this also, or you can make assumptions for different cars also. Okay, Omkar is asking if vehicle wheelbase is maximum, then how to achieve 100% of Ackerman in that case? What do you mean maximum? If it's beyond some point, your Ackerman angle will be very less, and that's how you will achieve 100% Ackerman. Sagar is asking, is there any reverse effect from front wheel to steering wheel in power steering car? So you're asking about if there's a force transfer from the road wheels to your steering wheel in power steering cars. Yes, there is, but the effect is very low. So you can probably feel whenever you're driving a power steering car, you can feel the bumps and all those things in your steering wheel. Whenever you go through a bump, you'll feel the steering wheel turn in your hand, but it's very low compared to a manual car. Gauss is asking, what if the steering axis lies on the contact patch of the tire? That is the zero scrub radius region. First of all, it is impossible to use. See, the thing is, we can never be, perfect pinpoint when we do this kind of things. We can either have positive scrub radius or negative scrub radius. When you have positive scrub radius, it's inside the tire, right? And if it's negative scrub radius, it's outside the center of the tire. And if it's negative, the effects are not that good. So you need to keep it positive for better calculation, all those things. So it's preferable to keep it positive and not at the zero, because in practical life it will never be at zero. It might go on the negative side also. Tushar is asking, sir, how autonomous vehicle steering works. Okay, so imagine we had the electric steering system, right? Yesterday I explained about the electric steering system. So imagine instead of steering wheel, the input is given by some AI as to how much to rotate the pinion. And that's how the autonomous vehicle steering works. Yeah, Raja is asking, due to slip, won't the tire undergo frequent stresses and tend to fail on frequent stretches of the rubber tire? Definitely. Whenever there's slip happening, the tires goes into wear and tear, and because of that, Formula One vehicles need to switch tires, frequently. If that was same done on commercial vehicles, we'd have to shift tires every time you reach somewhere, and that's not a good thing. That's why we use perfect rolling Ackerman steering mechanism. Arvind is asking, does backlash cause damage to the gear teeth in rack and pinion? And if it does, why is it mostly used? Okay, so backlash does cause some of the damage. It's called cavitation. It's called intermeshing or something like that. I don't remember the exact word. But what happens is, because of the friction between these things and the space that is there, and if you tend to push it a little bit, the impact force is very high, and that might cause the damage to rack and pinion. But that is again reduced by using helical gears. So the damage in the backlash is not that much if you use helical gears. Tarun Vishnu is asking, is the large change in steering system of 3-wheel auto having a steering wheel compared to 4-wheel? Okay, so in an auto rickshaw or even on a bike, the steering ratio that you have is 1:1. Okay, so if you rotate your handle by 1 degree, your tire will also rotate by 1 degree. But in your car, your steering ratio is more than 1, right? It's up to 4, 5, 6. So in auto rickshaws and your bikes, you have the steering ratio as 1. So it's definitely different. Okay, Madhur is asking, in Mercedes-Benz S-Class, they have a rear wheel turning a bit. So how does that affect the steering geometry? Okay, so that's a very different concept, and I would like to get into that, but it'll take some amount of time. But just to give you a brief, what happens whenever you are turning, right? The rear will tend to slip. Okay, whenever you're turning, even in perfect rolling condition, I mean not in perfect rolling condition, but in commercial vehicle, whenever you're turning, the rear will tend to slip, and to avoid that slippage, right? To avoid that slippage, the rear wheels are electronically controlled, and they change slightly the angle of the rear wheel so that they don't slip, to overcome the slip angle in the rear wheel. That's it. That's all they do in the Mercedes-Benz S-Class. Okay, Kunal Chaudhary is asking, which steering system is safe for selection, Ackerman or anti-Ackerman? It completely depends upon your application. If you have a Formula One race car, you should go with anti-Ackerman. If you have commercial vehicle, you should go with Ackerman geometry. Prashant is asking why resistive force is 1.4 and is all no. Okay, so resistive force is not 1.4. 1.4. The frictional coefficient between the road and tire was 1.4. For ATV, it's above 1, and for commercial vehicles, somewhere around 0.7. And for Formula One, it's probably even lesser than that, 0.6 or 0.63 probably. So you'll have to check for the vehicle type that the vehicle you're designing, and accordingly you have to select these coefficient of friction. Does contact patch, okay, Vasu is asking, does contact patch area effective? Definitely. So whenever you have lateral load transfer, why you get higher grip on the outer wheel is because there's a higher contact patch, because the tire is deforming more, because there's a higher load. So essentially when the car is loaded, the tire will deform more and the contact patch will increase, and that's how the grip will increase. Kashiram is asking, if anti-Ackerman is used in heavy vehicle, then what would happen, right? So if anti-Ackerman is used in heavy vehicles, first of all, the tires will burst out left and right. For each turn there, they would have to change the tire. Secondly, it wouldn't work that much because lateral load transfer is not as much as it happens in Formula One vehicle, because the speed is very low. However, I'll explain the slip once again and slip angle. Okay, Ansari Tanvir is asking, centripetal force occurs due to, okay, centripetal force occurs to counteract your centrifugal force. Okay, so whenever, if you're sitting on a chair, you have multiple forces applying onto you, right? There's a gravitational force applying to you, and there's a wind force, there's aerodynamic forces applying to you. So let's talk about the gravitational force, right? You're being pulled towards the earth, but you don't keep falling forever and ever. You stop falling because the chair you're sitting on or the seat you're sitting on is applying the inverse force which is pulling you down, right? So it will apply equal and opposite force in the opposite direction than the gravity. So that's how you don't keep falling. Similarly, if there's a centrifugal force and the vehicle is not moving away from the track, there's some other force contracting it, and that force is called centripetal force. Okay, Sean is asking, in which type of geometry, Ackerman or anti-Ackerman, we can do better drift. We can do better drift on anti-Ackerman geometry, definitely. It will be much like, it definitely depends upon slip angle, right? So if you have if you arrange your geometry in such a way that you let slip angle overtake your turning angle, in that case your vehicle will slide more and the centrifugal force will be more than your centripetal force, and you can drift better. Okay, Adinath is asking, when obstacle comes below the road wheel and the road wheel gets displaced, but the steering wheel does not get displaced, right? So this happens because there are suspension or shock absorbers placed in the tie rod. So whenever there's a bump in the road, the tie rod absorbs some of the shocks before sending it to the steering wheel. Okay, Vinayak is asking, is the tire patch same for the both wheels? No, it's never same for the any of the four wheels. It will be different slightly. And when there's a lateral load transfer happening, wherever there's more load, the tire contact patch will be more over there. Okay, Aniket is asking, is there any effect on rear wheel on steering effort? Both rear wheel steering effort. I don't think the steering effort is dependent on the rear wheel in Ackerman and the anti-Ackerman geometry. What should be the value of addendum and dedendum for clearance? Okay, these are empirical relations. You can look it up for different types of gear of different applications. Essentially, it's somewhere around, I guess, 25% of clearance, if I'm not wrong. Yeah, Mohammad Riyal, if you have anti-Ackerman geometry in your car, the drifting will be better. Okay, Drupad is asking what assumptions we should make while considering the calculation for steering in go-kart. Okay, so essentially you'll start with your wheelbase and track width. Then you will have, since you use drop link mechanism, you'll directly go to the drop link, the tie rod, and your Ackerman arm directly, and then you can calculate with geometry instead of rack. You directly connect your tie rod to the drop link, and whatever rotation is happening with your whatever rotation is happening with your drop link will replicate the motion of your pinion, and instead of rack, you will directly have your tie rods. Okay, Raja is asking to calculate the slip angle. We don't have any explicit formula, but we only with some software. Okay, it is not completely like that. Not just by software. You can calculate it theoretically, but it's very tedious process. You need to do your integration, derivation, and all those things. But it's better to have a experimental approach to it. What companies do when they manufacture tire, they do experimental tests on the tire. They plot out graphs, and based on those graphs, they create softwares which will essentially give out the data you need. Tushar is asking why do we use carbon fiber in F1? Basically to reduce the load and to create complicated shapes. Okay, Pratik is asking how the surface of push rod cross section looks like in F1 car. So if you want to see how it looks like, you can simply search aerodynamic aerofoil shape. Okay, aerofoil shape, and that's how everything in Formula One looks like. Pulkit is asking why supercar use carbon fiber monocoque. Okay, because they want to reduce the load. That's it. That's the only reason they use carbon fiber. Okay, Raja is asking how could you manage the clearance between rack and pinion? Very good question, Raja. The casing of rack and pinion is made in such a way that pinion and rack are always maintained at a perfect clearance. Okay, this is a question from unknown Mercedes railway sharing system, how it's managed. It's electronic. They do very, very slight changes. I'm guessing you're talking about Mercedes-Benz S-Class, and in that they do very, very small changes in the rear wheel toe, basically. So that's how they manage the rear wheel steering. Adarsh is asking which device is used to measure the slip angle. It's not a device, it's an experimental process where you can find out if you apply some amount of load and if you turn the wheel, how much it is turning and at which direction the tire is deformed. So with that, you can calculate the slip angle. There's no particular device that I know of, but I just know of the method. I think he's asking, are there any trusted website for vehicle dynamics? I would say ETG. But also, if you want journals and papers and research papers, all these things, I guess you can go to any of the famous journals like Elsewhere and Science, right? You'll find trusted research papers. If you want books, you can go to you can start with Kirpal Singh. You can look for books that formula students use, like FEA Supra and FEA Baha people use, and those are some of the books, some of the very good books that you can use for vehicle dynamics. Shashwat is asking, does front wheel and the rear wheel drive affect the steering of the vehicle? No, it actually does not affect the steering of the vehicle. Even if you have front wheel or the rear wheel drive, steering will affect in the same way. So yeah, that's I guess that's all for the doubts, and now we'll move on to the scholarship section. So I hand it over to Umang sir.
Thank you, Arbaz sir. Thank you, Arbaz sir. So we will be just going to play a message from company CEO Mr. Mayank. So he got held up with some work, otherwise he had planned to join. So I am going to have his video played. Just give me 1 second. Right after that, we will have the scholarship exam started. The video is for around few minutes. Okay. So here we go. So video is for 5 minutes only. And
thank you, Arbaz. Thank you for your wonderful session. And I believe every one of you got to learn a lot related to the steering dynamics and vehicle dynamics from Mr. Arbaz in last 2 days. Now, the next thing which we are going to have is the scholarship test. This test is very important for you because it will actually gonna give you a lot of opportunities to get skilled by having most of your fees for any of the program which you go for reduced as a scholarship amount. So I believe that what all you have learned in last 2 days, by giving the scholarship test, you could actually revise your learning and validate your learning by seeing how much you remember, how much things you have grasped, and we try to make a quiz where we cover all the topics which are covered in last 2 days, today and yesterday's session. So that is one thing. It can be a test for many of you, and it will be the results of that will turn out with a scholarship opportunity. So now what we are going to do, I am here to do an announcement. Myself, Mayank Arora, I am the founder of Elite Techno Groups. We decide ki how we are going to tell you the scholarship results. One thing is that we'll mail it to you. The other thing is like we share a board leaderboard where you will get to know about it. But if even if you get the scholarship results, are you clear enough how and where you can use it? How, which program you should go for by using the scholarship, which program is for whom, and how you can analyze the right program or right course for you, which will help you to achieve your career goals, because many of us don't even have the clarity of it. So we decided to do an exclusive webinar. It's a live interaction on Google Meet, where you will have full authority to speak, unmute yourself. We will discuss, you will ask your questions about your career goals, what you're looking forward to learn, how you want to achieve it. So we are going to do an exclusive webinar, which we call it as like scholarship results announcement and webinar on, are you an engineer liked by the industry? If not, how you can be. So this is the topic, and what all we are going to cover in it. First is the scholarship results. Second is how you can avail the scholarship. Okay. Third, detailed explanation of all ETG's industry-oriented internship cum training program, nano degree program. You have doubt related to it, how to go for it, what all you are going to learn, all those things. Fourth, journey of engineering, a student perspective versus industry's view. Okay, how you see your 4 year of engineering, how industry see you as an engineer. I'm actually going to show you a lot of details about it. Okay, next, how hiring is taking place in 2021, how hiring is taking place in 2021, how this pandemic have changed the whole hiring structure, process, expectations, and basically how you will get an opportunity if companies are not coming to your campus in future, not only this year but in the coming next 2 3 years, how the whole structure is going to be revamped. Usually till now it was more of campus placements. Within next 1 or 2 years, how things are going to drastically change, which we are seeing even this year. Now there are not much campus placements going on. It's more of a generic open hiring, and there are a lot many things which we're gonna discuss in this. Next is the gap between you and your skill set, the gap between you and your uh, career goals, the gap between college and academics, sorry, the college and industry. And there's a lot of gap which is not between college and industry, but there is a lot of self gap. So we are going to analyze that as well. Next, what are the future technologies you should aim to learn from an internship? If you're going for an internship, then what you should go for, which are best, which are futuristic, which are in demand, which will get you an opportunity to be placed in a good organization, to get good admission in higher studies, all that. And last, doorway to get your dream college or your dream job. What is the exact, or I say, what we have realized in last 8 years of our experience, that what is the doorway, what are the process, what are the steps, what are the initial beginning stepping stones which you should keep dedicatedly in this time when you have, so that you don't have to struggle to get a job or to get admission for your higher studies, or even have no clue if you want to start anything for your business, startup, any idea. It can be technical, non-technical. We are there to help you on that as well. So this webinar is going to happen tomorrow, where it will be at 4 p.m. That is 11th of July. That is Sunday. Joining link will be given to you in the comment section below. Okay. So everyone of you, I request, just after I'm about to complete, after this you will get your scholarship test. Do that dedicatedly. See you at tomorrow 4 p.m. so that we can share the results with you, and we can talk about all these topics in detail in this tomorrow's webinar. It will be on Google Meet. Okay. Take care. Thank you, everyone. Bye bye.
Hello guys, so I'm just going to start the live chat session here. Okay, so with this, just give me a second and I would be sharing the quiz timing. So before quiz timing, let me add a few more things here. So quiz timing would be 20 minutes. Okay, this is Umang here. I'm sharing the quiz link here. So I would also be putting what do you say? After quiz link, come back to the chat. We have few more things. Okay, attendance link would be shared after the quiz link. Okay. So quiz link is out. Time starts at 7:20 and it would end at 7:40. Okay. So right now I am increasing the timing in the chat here. I am increasing it to 200 seconds. Please don't what do you say? Message on the link. I am also sharing my screen with the timestamp. Okay, so 20 minutes left. You guys can start the quiz. There are two sections in the quiz. First section is where you would have the main quiz, the questions. It would take 15 minutes to do that 25 questions. Then next 5 minutes is the certification form. That's part of the quiz form itself. Okay, so attendance link is in the quiz form. You need to do the quiz to get the attendance. So I have also mentioned the details in the chat here. Okay, so I am sharing my screen with the live timer. Okay, 1 minute is already gone. So let's start the timer. Timer is for 20 minutes. It has started. I am sharing my screen so that you can see the timer here. Okay, so there goes the timer. Hi all, last 2 minutes left, or rather 1.5 minutes left. So while others are completing, I think we'll wait for just 1 more minute, let others complete. Then we have a quick few announcements to be made. I won't take much of your time on that. Okay, so we'll just quickly jump on that then. Okay, here I am, last few more seconds left, and then we jump into the things. Okay, I do see a lot of details are there, so the time's up. I am just closing. Okay, and I am about to close the link. So the link is closed now. Anyone who is filling, just submit it right away. Just 10 more grace period I am going to allot here, and then we are done. Everyone needs some grace period, right? There are always people with some kind of work left. So just few more seconds, and I think we are closing it here. Okay, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, and now we have closed it. Okay, so with this essentially now the next point is what next. Okay, so one thing is take the pledge. At Elite Techno Groups we are taking a pledge to be a skilled engineer. Okay, I have put the pledge in the description as well, and also I have added the joining link for sponsorship, scholarship in the description. Okay, so the idea is the link of the pledge is also given on Instagram. You can check that on our Instagram at ET Groups. Okay, and I hope you guys enjoyed the session. The main part of the session was to help you get started. Since we had quite a few folks joining in, the time is that yes, we had to take everyone's doubt, and the timing took part. So that was there. Next week is exciting. Okay, we have Aether. I hope everyone knows Aether Energy, right? We have the product designer head of Aether, Mr. Arun Vinayak, joining in. So he has left Aether and he is starting his own firm, which is Exponential Energy. Okay, he is going to be talking about what had been the innovations at Aether and what are the next things he is going to do. Then we have Royal Enfield's electric vehicle head, Mr. Allah Baksh, joining in. Okay, so next week is going to be all electric vehicle. Then we have another company's founder, Mr. Swastik, who is developing for physically disabled people, he is developing transformational wheelchairs. It goes by Neo Motion. That is coming up. Okay, so next week is also very exciting. If you are already part of Elite Techno Group's WhatsApp group, awesome. If you are not part of Elite Techno Group's WhatsApp group, okay, just drop us a message on info@elitetechnogroups.com. Okay, and we will send you the joining links. Okay, so this mail ID is also something which you can always use to interact with us. Okay, many people have doubts for certificates. Certificates for this session will be provided within a week. It's not accepting your form because the thing is that we have closed it, the time is done. Okay, any questions you have on Byte or anything you want to us for us to conduct, we will take it up. We might do it after Byte. So Byte is all about taking what students want, helping them learn the skills which are relevant for industry. We want you to be skilled, okay, and that's what drives us. Okay, so keep following us on Instagram. We keep updating all the details over there. You can subscribe us on YouTube. All the sessions would be live on YouTube so that you don't miss it. Add the reminder, so any session which is coming up, you can essentially be a part of those sessions. Okay, and if you have any questions related to the work we do at Allied Techno Groups, you could ask me. And else, I think the first part of the bite is complete, but it has just started. Next 3 parts of the bite are electric vehicle, Python and machine learning. Okay, and we will keep adding more courses. Okay, so that's all. And Sairam, yes, there are people who still want to understand and things. It has been 3 long hours. I hope it was helpful. We didn't ruin your 3 hours, so we are always there to help you guys. Prasad, that would be done on the merit of the questions. The toppers will get it free. Then there would be a substantial, a percentage to what ETG scholarship you will get. Okay, what is internship actually, Adinath? Very good question. Internship is technical training plus projects given to you as an internship program. All the details will be discussed in tomorrow's session. The details for tomorrow's sessions are already added in the description, and you would have got it by submitting the form as well. Okay, Madhura, the attendance link is part of the quiz itself, so it's done. Your friend has asked, organize a session on finite element method and analysis. So we are already coming up with a course on that. Also, we will organize that also. Would you please start coding? Vinayak, that is coming on 23rd, 24th and 30th, 31st. And we have an engineer who works in the core team of Google at USA. Okay, he is part of the one of the sessions which is going to be on 25th. He will walk you through also how things work. Another expert we have is a Stanford graduate on machine learning. He would also be teaching you guys on things. So we have an exciting list of people coming up in coming few days. Okay, so if you haven't already been joined part of the group, you could mail us. We will send you the joining link. And if you have any questions, any further queries, you can drop us. Again, I am sending you. You can go to our website, and there's a WhatsApp link also. Okay, go to Allied Techno Group's website and essentially drop us a WhatsApp. Okay. Okay. So Chandna, yes, you could submit the internship one with us. Prashant, thanks a lot. We really appreciate people liking our effort. Most of the things we would try to give it for free. We want to help students, the community, as much as we can. Rohan, I'm really sorry. It was for limited time period. I cannot help on that now. Manish, you will get certificate in next week. Okay. With this, I would be signing off. Great to have you guys. Take care. Stay safe, keep biting, and take your pledge. Okay, the pledge is mentioned in the description. Take your pledge, be serious, keep the engineering chain going. Okay, please, let's see you in the next sessions then. Take care, bye bye.